1 second. That's how close humanity came to witnessing one of the greatest engineering disasters of the 21st century, instead of one of its most astonishing triumphs. On October 13th, 2024, as a 233-foot tall rocket booster descended from the sky at hundreds of miles per hour, carrying enough explosive propellant to level several city blocks, heading straight toward its launch tower with pinpoint precision, a single sensor on the vehicle detected something wrong. The computer, processing thousands of calculations per second, was one heartbeat away from issuing an abort command, from ordering the booster to divert and crash into the ground beside the tower, rather than risk a catastrophic collision that could destroy years of work in an instant. 1 second away from that decision, the anomaly cleared. The catch proceeded, and the world watched in stunned disbelief as giant mechanical arms, massive steeds, steel chopsticks extending from a launch tower, closed around the descending rocket and held it suspended in midair. Engines still glowing hot, smoke billowing around its base. The engineers in the control room erupted in celebration, not knowing yet how close they'd come to disaster. That detail would only emerge days later, revealed quietly in an internal debrief, a secret that makes the achievement even more remarkable. This is the story you're about to hear. Not the polished version for press releases, but the real one, complete with the terror and triumph, the explosions and breakthroughs, the hubris and humility that define humanity's most ambitious attempt to become a multi-planetary species. Because right now, as you read these words, there is a machine being tested in the coastal wetlands of Texas that stands taller than the Statue of Liberty, weighs more than 4 space shuttles combined, produces twice the thrust of the mighty Saturn V, and is designed to do something no rocket has ever done before: fly up to orbit, return intact, get refueled, and fly again within hours. Not days, not weeks, hours. The aerospace industry said it was impossible. The physics made it impractical. The economics made it fantasy. And yet it's happening right now. Test flight after explosive test flight. Each failure teaching lessons that bring the dream closer to reality. This is Starship. This is the machine that will carry humans to Mars or die trying. And the journey has been far stranger, far more dramatic, and far more uncertain than anyone outside SpaceX's walls could have imagined. Now, let yourself settle in. Take a slow, deep breath. Release whatever tension you've been carrying in your shoulders, your jaw, the back of your neck. Tonight's journey will take you from the edge of disaster to the heights of human achievement, through explosions that taught more than success ever could, through the minds of engineers who see failure not as defeat, but as data, through the transformation of science fiction into welded steel and controlled fire. And yes, we'll discover what really happened in that 1 second window that could have changed everything. Hello there, and welcome to Sleepable Science. I'm so glad you found your way here. Maybe you've had a long day filled with earthly concerns. Or perhaps you're the kind of person who likes drifting to sleep with stories of human audacity, of engineers who turn the impossible into the inevitable, of machines that push the boundaries of physics until those boundaries move. Either way, tonight's exploration is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened. Because tonight, we're not just talking about a rocket. We're unraveling the story of Starship, a machine so ambitious that its very existence defies decades of aerospace conventional wisdom. A vehicle that has exploded more times than it has succeeded, yet somehow continues to inch closer to a future where humans might wake up on Mars and look back at Earth as a distant blue star in the morning sky. Beneath the gleaming stainless steel exterior lies a revolution, not just in technology, but in philosophy, in economics, in the fundamental question of whether humanity's future lies solely on this pale blue dot, or whether we might, one day, look up at the night sky from multiple worlds. We'll travel gently from the deserts of Texas, where these machines take shape, to the vacuum of space, where they're tested, from catastrophic explosions that taught invaluable lessons to triumphant catches that made the impossible real. You'll hear of engines that burn methane at pressures no rocket has ever achieved, of heat shields made from thousands of hexagonal tiles, of orbital refueling operations that sound like science fiction, and of a vision to place 1 million people on Mars within our lifetimes. Some of what you hear tonight may surprise you, may challenge your assumptions about what a rocket can be, or at the very least, spark some curiosity as you drift towards sleep. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. The vision. Why Mars? The story of Starship begins not with metal or mathematics, but with a question that has haunted one man for decades. Why, in a universe of infinite possibilities, are we confined to a single planet? Elon Musk, the founder of SpaceX, has been asking this question since long before his companies made him one of the wealthiest people on Earth. As early as 2001, he was speaking at Mars Society conferences about the need to extend human civilization beyond our home world. By 2007, according to multiple reports, he had stated publicly his personal goal of enabling human exploration and settlement of Mars. This wasn't a passing fancy or a billionaire's whim. This was, and remains, the driving purpose behind everything SpaceX does. The reasoning, as Musk has articulated countless times, rests on a premise both simple and profound. Humanity shouldn't remain a single-planet species. Every organism that has ever existed on Earth while confined to a single location has eventually faced extinction. Asteroid impacts, supervolcanic eruptions, climate catastrophes, pandemics, or simply the slow degradation of environmental conditions all have wiped out countless species throughout our planet's history. Humans, despite our technology and intelligence, remain vulnerable to these existential risks. One sufficiently large asteroid, one global pandemic we can't contain, one cascading climate collapse, and our story ends. But there's another dimension to this vision, one that transcends mere survival and touches something deeper in the human spirit. Musk has often spoken about the need for humanity's future to be exciting, to be inspiring, to offer something more than just solving one crisis after another. In his view, life must be about more than problems and solutions. It needs to kindle wonder. He recalls the collective inspiration the world felt watching the moon landings, how those missions represented not just technological achievement, but a vision of human potential realized. A Mars landing, he suggests, could serve the same purpose for our generation and the next. A beacon showing that humanity can still dare to reach beyond its current boundaries. Now here's where the vision transitions from philosophy to engineering reality, and where the timeline becomes, let's say, optimistic. Musk has publicly stated that he believes SpaceX could land humans on Mars as early as the late 2020s, with the goal of establishing a self-sustaining city of 1 million people by the 2060s. When pressed on details, he's suggested that such a colony might achieve self-sufficiency, the ability to survive even if supply ships from Earth stopped arriving, within 7 to 9 years of establishment. These are, to put it mildly, aggressive projections. Most aerospace experts, even those who admire SpaceX's achievements, view these timelines with profound skepticism. But here's what makes Musk's approach different, and this is crucial to understanding Starship's development. Where traditional aerospace programs set conservative timelines and aim for nearly perfect execution, accepting that this makes progress slow, Musk deliberately sets almost impossibly ambitious targets, knowing full well they'll be missed, but using them to drive a pace of innovation that would be impossible under conventional planning. It's a calculated strategy. The real launch dates slip, the real milestones take longer, but the breakneck pace of development, the willingness to test, fail, learn, and fly again within months rather than years, this creates progress that traditional aerospace simply cannot match. The choice of Mars as the destination is not arbitrary. Of all the celestial bodies in our solar system, Mars is uniquely suited to human colonization, at least among the options realistically within our reach. It has a day length remarkably similar to Earth's, about 24 hours and 37 minutes. It has seasons, though they are roughly twice as long as Earth's. It has polar ice caps containing water. Its atmosphere, though thin and mostly carbon dioxide, exists and can potentially be utilized. Its gravity, though only 38% of Earth's, is substantial enough that we understand how humans might adapt to it, unlike the microgravity of space stations or the Moon's mere 16% of Earth gravity. Most importantly, Mars has resources that can theoretically support a self-sustaining colony. The regolith contains minerals. The atmosphere contains carbon dioxide that can be split into oxygen for breathing and carbon for manufacturing. Water ice exists at the poles and likely underground in many locations. Using a process called in situ resource utilization, a Mars colony could potentially manufacture its own rocket propellant, specifically liquid methane and liquid oxygen, the same propellant Starship uses, by combining atmospheric carbon dioxide with water. This is not speculation. NASA has successfully demonstrated this technology with the MOXIE experiment on the Perseverance rover. But establishing a Mars colony is not just about going there. It's about creating a civilization that can exist independently of Earth, a backup for humanity's consciousness and culture. According to reports from 2024, Musk has stated that being able to make use of local resources on Mars would be essential for establishing a self-sustaining colony, and that SpaceX intended a colony to develop self-sufficiency within 7 to 9 years of establishment. This is an extraordinarily ambitious timeline, but it drives home the scope of the vision. We're not talking about a research outpost like the Antarctic stations, dependent on constant resupply from Earth. We're talking about a genuine second branch of human civilization. The scale of this vision is staggering. The program aims to send 1 million people to Mars using 1,000 starships launched during Mars launch windows, which occur approximately every 26 months when Earth and Mars are optimally aligned. The journeys would require between 80 and 150 days of transit time, averaging approximately 115 days based on the orbital mechanics of the 9 synodic periods occurring between 2024 and 2041. Think about that for a moment. 1 million people, 1,000 spacecraft, regular flights departing during specific windows when the planets align. This is not space exploration as we've known it, with a handful of highly trained astronauts on rare missions. This is the industrialization of space, the beginning of human expansion into the cosmos. Musk's timeline for achieving this has evolved over the years, as is typical with such ambitious goals. In 2021, he stated he remained highly confident that SpaceX would land humans on Mars by 2026, though this has since been revised. More recent statements suggest first uncrewed missions potentially by 2026, taking advantage of the next Earth-Mars transfer window, followed by crewed missions within about 4 years if those initial missions prove successful. As of 2025, SpaceX was targeting the 2026-2027 Mars launch window, with Musk estimating a 50% chance of being ready in time, pending successful demonstration of orbital refueling capabilities. These timelines may seem aggressive, even unrealistic to some observers. The history of spaceflight is littered with missed deadlines and delayed missions. But SpaceX has a track record that demands we take these goals seriously, even if skeptically. The company has consistently achieved what established aerospace companies said was impossible. They developed reusable orbital rockets when the industry said it couldn't be done economically. They created the world's most powerful operational rocket, Falcon Heavy, using components from their existing Falcon 9. They became the first private company to send humans to orbit and to the International Space Station. They catch rocket boosters from the sky. The vision extends beyond even Mars. Musk has described the Red Planet as a stepping stone, a first step toward making humanity a multiplanetary species. Once Mars is colonized and serves as a second center of human civilization, the technology and experience gained could enable journeys to other planets in the solar system. Eventually, perhaps, to other star systems entirely. This is thinking on a civilizational timescale, planning not for the next quarter or the next election cycle, but for the next century and beyond. Critics have raised valid questions about this vision. Is it ethical to spend billions on Mars colonization when Earth faces pressing challenges like climate change, poverty, and disease? Musk has acknowledged these concerns, but argues that becoming a multiplanetary species is not a diversion from solving Earth's problems, but a parallel effort that can inspire technological innovation, create jobs, and address existential risks to humanity. The technologies developed for Mars colonization, from advanced life support systems to in situ resource utilization, could have applications here on Earth. There's also the question of whether Mars is truly habitable in the long term. The planet has no magnetic field to protect against cosmic radiation. Its atmospheric pressure is less than 1% of Earth's, making it impossible to survive on the surface without a pressure suit. The soil may contain perchlorate toxic to humans. These are not insurmountable obstacles, but they are serious challenges that will require solutions we haven't fully developed yet. And yet, the vision persists. It persists because it offers something rare in our modern world. A goal that unites rather than divides, that inspires rather than cynically calculates, that reaches for the stars rather than settling for incremental improvements. Whether Starship successfully lands humans on Mars in 2028, 2030, or 2040, whether the first colony has 1,000 people or 1 million, the mere pursuit of this goal has already changed what we think is possible. It has already sparked innovations that ripple through the aerospace industry and beyond. It has already inspired a new generation to study engineering, to dream of distant worlds, to believe that the future might be extraordinary rather than merely survivable. As you drift toward sleep tonight, imagine it. Imagine looking up at the night sky, not from Earth, but from Mars, seeing our blue home world as a distant star in the blackness. Imagine watching a starship descend through the thin Martian atmosphere, carrying the supplies and people needed to build something new, something that has never existed before, a second home for humanity among the stars. That vision, more than any engineering specification or budget projection, is what drives the development of Starship. It is the dream that turns steel and fire and careful calculation into the most powerful rocket ever built. And it is the reason why, on quiet Texas mornings, these massive machines rise on pillars of flame, reaching for orbit, reaching for the moon, reaching ultimately for Mars. Engineering marvel, anatomy of Starship. Stand at the base of a fully stacked Starship on the launch pad at Starbase, and you have to crane your neck to see the top. This machine is colossal, a monument to human ambition rendered in gleaming stainless steel. When the Super Heavy booster and Starship spacecraft are combined, the full stack stands approximately 121 meters tall, about 398 feet, roughly the height of a 40-story building. To put this in perspective, it towers over the Statue of Liberty, which reaches 305 feet from ground to torch. It is the tallest rocket ever built, surpassing even the legendary Saturn V that carried astronauts to the moon, which stood 363 feet tall. But height alone doesn't capture the scale. When fully fueled and ready for launch, the complete Starship system has a mass of approximately 5,300 metric tons. That's about 11.7 million pounds. Most of that mass, roughly 4,600 metric tons of it, is propellant, the liquid methane and liquid oxygen that will be consumed in minutes of thunderous combustion. The vehicle's diameter is 9 meters, or about 30 feet, wide enough to comfortably fit a small house inside, which is precisely what SpaceX has done with the crew cabin designs in some variants. The sheer volume available inside this machine is staggering. Approximately 1,000 cubic meters in the payload area, enough to transport an assembled space telescope, prefabricated habitat modules, or 100 people with their life support systems and supplies. Let's start at the bottom and work our way up, because that's where the power lives. The Super Heavy booster is the first stage, the massive cylinder that will burn for just a few minutes to heave the entire stack out of Earth's gravity well. This booster stands 71 meters tall, about 233 feet, and is composed of 4 general sections: the engine bay at the bottom, the liquid oxygen tank, the liquid methane tank above that, and the inner stage at the top that connects to the Starship second stage. The propellant tanks are separated by a common bulkhead, a structural dome that keeps the two cryogenic liquids apart, a design similar to the one used on the Saturn V's upper stages. The engine bay is where the magic happens, or more accurately, where controlled explosions happen at a rate and intensity that boggles the mind. Super Heavy is powered by 33 Raptor engines. Let that number sink in. 33 rocket engines, all firing simultaneously, all perfectly coordinated, all producing over 2 meganewtons of thrust each. The total thrust at liftoff is approximately 7,590 tons force, or about 74.5 meganewtons. For comparison, the Saturn V produced about 35 meganewtons of thrust at liftoff. Starship Super Heavy produces more than twice that, making it by far the most powerful rocket booster ever flown. The sound alone is extraordinary. Observers miles away report feeling the vibrations in their chests, a physical sensation of power that is difficult to describe to those who haven't experienced it. The engines are arranged in a specific configuration. The outer ring contains 20 engines that cannot gimbal. They point straight down and fire at full thrust. These provide the raw pushing power needed to lift the vehicle. The inner ring contains 13 engines that can gimbal up to 15 degrees, allowing them to vector their thrust for steering and control. This gimbaling capability is crucial for keeping the rocket stable and on course during ascent. If you watch a Starship launch, you can sometimes see these inner engines moving slightly, making constant tiny adjustments to keep the massive stack pointed in the right direction despite winds, weight shifts, and the complexities of supersonic flight through the atmosphere. After stage separation, Super Heavy faces an even more challenging task: returning to the launch site. To do this, it performs what's called a boost-back burn, using 13 of its engines to reverse its trajectory and send it back towards Starbase. Then comes the landing burn, which has evolved dramatically over the course of Starship's testing. Initially, SpaceX planned for the booster to land on legs like the Falcon 9, but Musk and his team realized that legs add weight, require refurbishment, and slow down the turnaround process. So they developed something audacious instead. They would catch the booster with the launch tower itself, using 2 massive mechanical arms nicknamed the chopsticks. We'll explore this innovation in detail later, but for now, know that it represents a fundamental reimagining of how rockets can be recovered and reused. Now let's move to the second stage, the part called Starship, which confusingly is also the name for the whole system. This spacecraft sits atop Super Heavy and is what actually goes to orbit, to the moon, or to Mars. The Block 2 version of Starship, introduced in 2025, stands 52.1 meters tall, about 171 feet, making it taller than the Space Shuttle orbiter, and more voluminous than any spacecraft ever built. Like Super Heavy, it's 9 meters in diameter and composed of several sections: the engine bay at the bottom, the liquid oxygen tank, the liquid methane tank, and the payload bay at the top. Starship is powered by 6 Raptor engines, 3 Raptor engines optimized for sea level with smaller nozzles, and 3 Raptor vacuum engines with larger nozzles designed for efficiency in the vacuum of space. During launch, all 6 engines fire to push Starship away from the booster during hot staging, a maneuver we'll discuss shortly. Once in space, the 3 vacuum engines take over for orbital maneuvering and the burns needed to boost toward the Moon or Mars. Each of these engines is a marvel of engineering that we'll explore in depth later. But for now, appreciate that they represent the cutting edge of rocket propulsion technology, operating at chamber pressures higher than any rocket engine has ever sustained. The exterior of Starship tells a story of radical reinvention. The entire vehicle, both Super Heavy and the Starship spacecraft, is made of stainless steel. This wasn't the original plan. In fact, when SpaceX first began seriously developing what would become Starship back in 2016 and 2017, the design called for advanced carbon fiber composites, the same lightweight material used in Formula One racing cars and high-end bicycles. Carbon fiber seemed perfect for a rocket, incredibly strong for its weight, able to be formed into precise shapes, representing the cutting edge of aerospace materials technology. SpaceX even built an enormous tent in Los Angeles, where workers laid up carbon fiber sections for early test tanks. Then, in late 2018, Elon Musk made an announcement that stunned his own engineering team and bewildered the aerospace community. They were switching to stainless steel. Engineers who had spent 2 years perfecting carbon fiber fabrication techniques learned their work would be scrapped. The massive composite manufacturing tent would be abandoned. The careful weight calculations would need to be redone. Why make such a dramatic pivot so late in development? Musk's reasoning, as he explained in presentations and interviews, was characteristically unconventional, but, in retrospect, brilliant. First, stainless steel is cheap and easy to manufacture compared to carbon fiber composites. It can be welded with standard equipment by skilled workers, whereas carbon fiber requires expensive autoclaves, precise temperature control, and specialized expertise that's rare and expensive. The cost difference was staggering. Carbon fiber might cost $135 per kilogram, while 304 stainless steel costs about $3 per kilogram, a factor of 45 times cheaper. Second, and this is where the physics gets interesting, stainless steel becomes stronger at cryogenic temperatures. Most materials become brittle when you cool them to the temperatures of liquid oxygen and liquid methane, stored at roughly minus 183 degrees Celsius and minus 162 degrees Celsius respectively. But the specific steel alloy SpaceX selected actually gains tensile strength as it cools, meaning the propellant tanks themselves make the structure stronger rather than weaker. This property allowed SpaceX to use thinner steel than would be needed at room temperature, partially compensating for steel's greater density compared to carbon fiber. Third, stainless steel can withstand intense heat, crucial for re-entry. The 300 series stainless steel SpaceX uses can endure temperatures up to 1,500 degrees Celsius before losing structural integrity. While that's not enough for the full force of re-entry, which can create temperatures exceeding 2,500 degrees on the vehicle's leading edges, it provides a robust foundation for the thermal protection system and can handle minor failures or gaps in the heat shield that would catastrophically destroy a carbon fiber structure. And perhaps most importantly, from a development standpoint at least, stainless steel allowed SpaceX to build and test rapidly. You can weld up a steel tank section in days. Carbon fiber layup and curing takes weeks. when you're following a rapid iteration philosophy, where speed of learning matters as much as final performance, that difference in fabrication time is transformative. The switch to steel, though shocking at the time, accelerated Starship's development by years compared to what would have been possible with carbon fiber. The decision proved prescient. Had Starship been built from carbon composites, the early test flights, with their explosive failures and hard landings, would have been far more expensive. Each destroyed prototype would have represented months of careful composite layup work. With steel, SpaceX could afford to build, test, explode, and build again, learning at a pace that would have bankrupted a composite-based program. But stainless steel alone isn't enough to survive re-entry. When Starship comes back through Earth's atmosphere at orbital velocities, it faces temperatures that would melt most metals. The solution is a thermal protection system consisting of about 18,000 hexagonal heat shield tiles that cover the windward side of the spacecraft, the side that faces the oncoming air during re-entry. These tiles are made of a silica-based material that can withstand temperatures up to 1,400 degrees Celsius. They're attached to the steel skin with pins and small gaps between them to allow for thermal expansion. Each tile is precisely shaped and positioned, creating a smooth surface that helps manage the flow of superheated plasma around the vehicle. The tiles have been a continuing challenge for SpaceX. During early flight tests, dozens or even hundreds of tiles would fall off during ascent or re-entry. After Flight Test 4, engineers added a secondary ablative layer underneath the primary heat shield, providing backup protection if tiles are lost. After Flight Test 10, they added a felt material nicknamed the crunch wrap between the gaps in the tiles to prevent hot plasma from seeping through and damaging the steel underneath. These iterative improvements made flight after flight exemplify SpaceX's approach to development. Fly, fail, learn, improve, fly again. Starship also features 4 flaps for controlling its attitude during re-entry and landing. 2 forward flaps are mounted near the nose, and 2 aft flaps are near the engine bay. These flaps serve multiple purposes. During re-entry, Starship performs a controlled descent in a belly flop orientation, falling horizontally like a skydiver. The flaps act like small wings, allowing the spacecraft to glide and steer as it descends through the thickening atmosphere. The aft flaps also produce drag, helping to slow the vehicle. Then, just before landing, Starship performs a flip maneuver, rotating to a vertical orientation and firing its engines for a propulsive landing. It's an unconventional approach that saves weight by not requiring wings or parachutes, but it requires extraordinary control authority, which the flaps provide. The flaps have also proven challenging. During Flight Test 4, the forward flaps suffered severe damage from heat and plasma during re-entry, with one flap nearly burned through. For Block 2 vehicles introduced in 2025, SpaceX redesigned the forward flaps, moving them to the leeward side of the vehicle where they would experience less heating, making them thinner and angling them differently to reduce the forces they experience. These changes demonstrate how SpaceX learns from each flight, incorporating lessons directly into the next iteration of hardware. Inside Starship, the layout depends on the variant. The cargo version features a large payload door that opens in space to deploy satellites or other cargo. The tanker version is filled almost entirely with additional propellant tanks, as its job is to rendezvous with other starships in orbit and transfer fuel for missions beyond Earth orbit. The crew version, designed to carry up to 100 people to Mars, includes a pressurized cabin with life support systems, sleeping quarters, a galley, and facilities for the long journey. NASA's Human Landing System version, designed for the Artemis program to land astronauts on the moon, features a specialized configuration with an airlock for moonwalks, a docking port to connect with the Orion spacecraft, and an elevator to lower astronauts to the lunar surface from the crew area, which sits about 30 meters above the ground when Starship is standing on the moon. The propellant capacity of the full stack is enormous. Super Heavy carries about 3,600 metric tons of propellant, while Starship carries about 200 metric tons, for a total of roughly 4,800 metric tons. During a launch to low Earth orbit, nearly all of this propellant is consumed. Super Heavy burns through its fuel in about 2.5 minutes, reaching an altitude of around 70 kilometers before separating from Starship. Starship then continues burning its engines for several more minutes to achieve orbital velocity. The precise amount of propellant consumed depends on the mission profile, the payload mass, and other factors. But launching 100 to 150 metric tons to orbit requires burning vast quantities of fuel. To enable missions beyond Earth orbit, Starship uses orbital refueling, a technology that has never been demonstrated with cryogenic propellants in space. The concept is straightforward, at least in principle. A Starship heading to the Moon or Mars launches with a full load of payload but nearly empty tanks. Then, multiple tanker Starships launch and rendezvous with it in orbit, transferring propellant until the main mission vehicle is fully fueled. Estimates vary, but SpaceX CEO Elon Musk suggested that 8 tanker launches might be needed to completely refuel a Starship in low Earth orbit, though some estimates suggest as many as 20 refueling flights might be required for a Mars mission, depending on the exact trajectory and payload. This sounds cumbersome, but if Starship can achieve rapid reusability with quick turnarounds, launching 8 or even 20 times over a few weeks becomes feasible. As you imagine this machine in your mind, picture it not as a static monument, but as a dynamic system. Fuel sloshing in its tanks, engines firing in precise coordination, computers making thousands of calculations per second to adjust trajectory, structure flexing and creaking under immense loads, heat shields glowing orange and white as they ablate away microscopic layers, absorbing the fury of re-entry. Starship is not just large. It is complex, a symphony of engineering where every component must work in harmony with every other, where failure in any single system can cascade into catastrophe, and where success represents the culmination of decades of human knowledge about materials, propulsion, guidance, and a dozen other disciplines. And yet, for all its complexity, Starship is designed to be mass-produced. SpaceX is building these vehicles in something resembling an assembly line at their Star Factory facility in Boca Chica. Musk has stated that the company can now produce a ship roughly every 2 or 3 weeks, and they are ultimately aiming for the ability to produce 1,000 ships a year, which would be 3 ships a day. Whether they achieve that rate remains to be seen, but the very fact that they are designing for it, that they are building manufacturing infrastructure to support it, tells you something profound about how different this approach is from traditional aerospace development, where spacecraft are often hand-built one-offs, requiring years of assembly. Let yourself imagine the factory floor, the smell of welding and steel, the sound of machinery shaping metal into cylinders, the sight of multiple starships in various stages of assembly, some just rings of steel being stacked and welded, others nearly complete with engines installed and heat tiles being attached. This is not how we've built spacecraft before. This is mass production, applied to machines that leave the planet. It is the industrialization of space access. And it is happening right now, in the swamps and dunes of South Texas, where the future is being hammered and welded into shape. Revolutionary design philosophy. To understand Starship, you must understand that it represents a fundamental break from how rockets have traditionally been developed. For decades, the aerospace industry followed a methodical, conservative approach. You design extensively on paper and in simulations. You build test articles and put them through grueling ground tests. You conduct wind tunnel studies and computational fluid dynamics analyses. You verify and re-verify every calculation. Only after years of this process, and only after you're absolutely certain everything will work, do you attempt to fly. And when you do fly, you fly conservatively, minimizing risk at every turn. This approach has given us reliable rockets like the Atlas V and Delta IV, which rarely fail. It has also given us rockets that cost hundreds of millions of dollars per launch and take a decade or more to develop. SpaceX has chosen a different path, one summed up in a phrase you'll hear repeatedly if you follow Starship's development: rapid, iterative testing. The philosophy is simple, almost brutally so. Build hardware quickly and cheaply. Fly it. If it explodes, figure out why, fix the problem, and fly again. Repeat this cycle as fast as possible. Learn from real-world performance rather than trying to predict every failure mode in advance. Accept that some vehicles will be lost, but minimize the cost of those losses by keeping the hardware relatively simple and the production pace high. This isn't recklessness. It's a calculated approach based on the recognition that complex systems always behave in ways you don't expect. And the fastest way to find those unexpected behaviors is to test in real conditions. Simulation and ground testing are valuable, but nothing fully replicates the environment of actual flight. The combination of vibration, acceleration, temperature extremes, and a dozen other factors that interact in ways too complex to model perfectly. Consider the early Starship prototypes, the vehicles designated SN5, SN8, SN9, SN10, and so on, SN standing for serial number. These were not carefully crafted one-offs, but mass-produced test articles, built in a matter of weeks at the Boca Chica facility. Starting in 2020, SpaceX began flying them on short hops, testing different aspects of the vehicle's capabilities. SN5 and SN6 conducted 150-meter hop tests, just enough to prove that the engines and basic flight controls worked. SN8 attempted the first high-altitude flight, reaching 12.5 kilometers before attempting a flip maneuver to land vertically. It didn't make it. The vehicle came down hard and exploded in a fireball. SpaceX learned from that flight and tried again with SN9. It also exploded. SN10 made it to the pad intact, but then exploded a few minutes later. SN11 disintegrated during descent. SN15 finally stuck the landing, becoming the first Starship prototype to fly to altitude and return intact. Each of these flights provided data that couldn't be obtained any other way. They revealed problems with the flip maneuver, with engine relight at altitude, with the interaction between the flaps and the body during descent. Traditional aerospace would have spent years in simulation trying to predict these issues. SpaceX found them in months of actual flight testing, and because they were building new prototypes continuously, they could incorporate fixes quickly. This approach extends to the full-stack flights that began in 2023. The first integrated flight test, often called IFT-1, took place on April 20th, 2023. It was, by conventional standards, a failure. The rocket lifted off, but 3 engines shut down during ascent, likely due to debris from the launch pad damaging their fuel lines. Several more engines failed during flight. The vehicle began to tumble out of control. About 4 minutes after liftoff, the flight termination system was activated. The vehicle exploded. You might think this would be seen as a catastrophe. Instead, SpaceX called it a successful test. Why? Because they gathered data on how the vehicle performed under real flight conditions. Data that would inform improvements to both the rocket and the launch infrastructure. And they did improve, rapidly. For the launch, they installed a water deluge system under the pad to suppress the intense acoustic energy and heat from the engines, reducing damage to the pad itself. They strengthened the propellant feed lines to make them more resistant to debris. They improved the engine shielding and fire suppression systems. All of these changes were implemented in a matter of months, not years. The second integrated flight test, IFT-2, flew on November 18th, 2023. This time, all 33 engines started successfully and completed a full-duration burn during ascent. Starship executed hot staging for the first time, where the second stage engines fire before the stages separate, giving an extra boost. The Super Heavy booster was lost during its return, experiencing multiple engine failures and exploding during the boost-back burn. The Starship's second stage reached space for the first time, but was lost near the end of its burn due to a fire caused by venting liquid oxygen. Again, partial success, but enough progress to justify moving forward. The third flight, IFT-3 on March 14, 2024, demonstrated even more capabilities. The booster again performed well, though it was lost during the landing attempt when it failed to relight enough engines. The Starship spacecraft opened and closed its payload bay doors in space, demonstrating cargo deployment capability. It transferred propellant between tanks, a crucial test for future orbital refueling. It attempted a re-entry and made it all the way to the Indian Ocean before breaking up, but it had survived long enough to gather valuable thermal protection system data. The fourth flight, IFT-4, on June 6, 2024, was the first where both stages survived to their intended splashdown locations. The booster executed a controlled splashdown in the Gulf of Mexico. The Starship spacecraft survived re-entry despite losing many heat shield tiles and suffering severe damage to one of its forward flaps. You could see the flap glowing red hot and partially burning through in the onboard camera footage. Yet the vehicle maintained control and achieved a soft splashdown in the Indian Ocean. This was a breakthrough, proving that the basic design could work even with significant damage. Then came Flight 5, on October 13, 2024, and everything changed. For the first time, SpaceX attempted to catch the Super Heavy booster with the mechanical arms of the launch tower, a maneuver many thought was foolishly risky for a first attempt. The booster separated from Starship, performed its boost-back burn, and returned to the launch site. As it approached the tower, traveling at hundreds of kilometers per hour, it fired its engines to slow down, performing a series of precise maneuvers to align itself with the arms. Then, in a moment that seemed to defy belief, the massive chopstick arms closed around the booster, catching it in midair and holding it securely above the pad. The control room erupted in cheers. "This is a day for the engineering history books," the livestream host said, and they were right. It was the first time a rocket booster had been caught out of the sky, and it fundamentally changed the calculus of reusability. Subsequent flights have continued this pattern of testing and learning. Flight 6 caught the booster again, but lost the ship during ascent. Flight 7 marked the debut of the upgraded Block 2 Starship, but exploded during ascent when the ship lost control. Flights 8, 9, 10, and 11 have each incorporated lessons from previous flights, testing new systems, refining the heat shield, improving the engines, working toward the ultimate goal of routine, rapid reusability. This brings us to the concept of full reusability, the holy grail of spaceflight that Starship is designed to achieve. Currently, most rockets are expendable, meaning they're used once and then discarded. SpaceX's Falcon 9 is partially reusable. The first stage booster can be recovered and reflown, but the second stage burns up during re-entry. Starship is designed to be fully reusable, both stages returning to Earth for reuse, and not just reusable, but rapidly so, with the goal of relaunching within hours or days rather than months. Why does this matter? Because the cost of spaceflight is dominated not by the propellant, which is relatively cheap, maybe a few $100,000 worth of methane and oxygen for a Starship flight, but by the cost of the hardware. If you throw away a rocket worth hundreds of millions of dollars every time you fly, each launch will cost hundreds of millions. But if you can reuse the same rocket dozens or hundreds of times, the cost per flight drops dramatically. You still have refurbishment costs, inspection, replacement of worn parts, refueling. but these are far less than building a new rocket each time. SpaceX estimates that if they can achieve full and rapid reusability, they could eventually reduce the cost per launch to just a few $1,000,000, maybe even less, making space access cheaper than it has ever been by orders of magnitude. This cost reduction would be transformative. It would make large-scale satellite constellations economically viable. It would allow more frequent missions to the Moon and Mars. It would enable entirely new categories of space activity, space tourism, on-orbit manufacturing, space-based solar power, even the large-scale colonization efforts that Musk envisions. Cost has always been the primary barrier to space development. Reduce that barrier sufficiently, and the possibilities expand exponentially. The philosophy of full reusability dictates every design decision in Starship. The choice of stainless steel instead of lighter materials makes sense when you plan to reuse the vehicle many times. Durability becomes more important than minimizing dry mass. The decision to catch the booster with the tower arms eliminates the need for landing legs, which add weight and require refurbishment. The use of methane fuel instead of the RP-1 kerosene used in Falcon 9 makes sense because methane burns cleaner, leaving less residue that has to be cleaned out before the next flight. The high engine count provides redundancy. If a few engines fail, the mission can still succeed, and the vehicle can still return safely. Even the testing strategy serves reusability. By flying prototypes rapidly and accepting losses, SpaceX keeps the cost of each individual vehicle low, which makes the economics of testing affordable. Compare this to NASA's Space Launch System, which has cost tens of billions of dollars to develop and has flown only twice as of 2025, with each launch costing over $4 billion. Starship development has cost SpaceX an estimated $5 billion total, spread over many years, and they've flown dozens of test vehicles in that same time. The rapid iteration approach is not just faster, it's cheaper overall, even accounting for the destroyed prototypes. As you let your mind drift, think about what this means. Think about a future where launching something to orbit is as routine as loading cargo onto a ship, where rockets land, get refueled, and fly again the same day. Where the barrier between Earth and space becomes not a vast economic gulf, but a manageable step. This is what Starship's revolutionary design philosophy is aiming for. Not just a better rocket, but a complete reimagining of how we access space. Turning spaceflight from a rare, expensive, high-stakes endeavor into something approaching routine transportation. And every flight, every explosion, every successful catch brings that vision a little closer to reality. The testing journey, explosions, and progress. There's something profoundly human about learning through failure. Children fall hundreds of times before they learn to walk. Inventors create countless failed prototypes before they hit upon a working design. And spacecraft, it turns out, explode. A lot. The path from concept to operational Starship is littered with debris fields, burnt metal, shattered tanks, and shredded fins. It is also paved with invaluable lessons, each failure teaching the engineers something they couldn't have learned any other way. So let's walk through this journey together, from the early hops to the latest orbital flights, and see what each step taught humanity about building the future of spaceflight. The story really begins with a small, stubby vehicle called Starhopper. This was never meant to orbit. It looked more like a water tower with an engine than a spacecraft. But on July 25, 2019, at SpaceX's facility in Boca Chica, Texas, Starhopper performed the first successful flight of a vehicle using a Raptor engine, reaching an altitude of about 150 meters before landing successfully. It was a humble beginning, a short hop that lasted less than a minute, but it proved that the Raptor engine could throttle, restart, and provide the control needed for vertical landing. That flight validated years of theoretical work on the engine design. Next came the serial prototypes, built and tested in rapid succession. These were full-height vehicles, approximately 50 meters tall, but they represented just the Starship upper stage without a booster. SN8 was the first to attempt a high-altitude flight, reaching about 12.5 kilometers on December 9, 2020. The ascent was perfect. The flip maneuver was executed beautifully, but one of the engines failed to relight for landing. The vehicle came down hard, hit the pad at an angle, and exploded in a massive fireball. Watchers online were devastated. Musk tweeted, "Fuel header tank pressure was low during landing burn, causing touchdown velocity to be high. We got all the data we needed. Congrats, SpaceX team." And that encapsulated the philosophy. They learned what they needed to learn. SN9 flew on February 2nd, 2021, reaching 10 kilometers. Again, the ascent and flip were successful. Again, an engine issue during landing. Both engines that were supposed to provide landing thrust failed to reach full power. The vehicle crashed and exploded. 3 weeks later, SN10 flew the same profile, and this time, it landed. For a few glorious moments, it stood upright on the pad, slightly tilted, but intact. Then, about 8 minutes after touchdown, a fire that had been smoldering in the engine bay reached a propellant leak, and the vehicle exploded. Still, it was progress. They'd proven the landing was possible. SN11 launched into heavy fog on March 30th, 2021, making it difficult to see what happened. The vehicle reached altitude and began its descent, but during the flip, something went wrong. Debris began raining down through the fog. The vehicle had disintegrated in midair, likely due to a fuel leak and engine explosion. SN15, incorporating lessons from all the previous flights, finally achieved what they'd been working toward. On May 5th, 2021, it flew to 10 kilometers, performed the flip maneuver flawlessly, landed softly, and stayed landed. There was a small fire at the base, but the vehicle survived. It still stands at Starbase, as of this writing, a monument to persistence. With the basic flight profile validated, SpaceX moved on to full stack testing, flying both the Super Heavy booster and the Starship spacecraft together. This is where the complexity increased dramatically. Now they weren't just testing one stage, but 2 stages, plus the staging event itself, plus the return and landing of both stages. The first integrated flight test, IFT-1, launched on April 20th, 2023. The sight was awe-inspiring. When 33 Raptor engines ignited simultaneously, the ground shook for miles. The vehicle rose on a pillar of flame that dwarfed anything previously seen in spaceflight. For a few seconds, it looked perfect. Then problems began. 3 engines shut down in the first few seconds, likely damaged by debris kicked up from the launch pad. You see, this was the first launch from the new orbital pad, and SpaceX had underestimated how much damage the rocket's exhaust would do to the concrete under the pad. The engines created a crater, sending chunks of concrete flying in all directions. Some of this debris struck the rocket itself, damaging fuel lines and heat shields. More engines failed during ascent. By the time the vehicle was supposed to perform stage separation, too many engines were offline. The rocket began to tumble. Hot staging couldn't work without proper thrust and control. The flight termination system was activated, though it took about 40 seconds for the explosives to actually destroy the vehicle due to some technical issues. The rocket disintegrated at an altitude of about 39 kilometers over the Gulf of Mexico. The internet lit up with commentary. Critics called it a failure, a waste of money, a demonstration of SpaceX's recklessness. But within the aerospace community, and among those who understood the test philosophy, the assessment was different. SpaceX had gathered extensive data on how the full stack performed, how the engines operated together, how the vehicle handled during ascent, what happened when things went wrong. And critically, they learned about the launch pad. The damage to the pad, while dramatic, taught them what they needed to do to reinforce it for future flights. Over the next months, SpaceX implemented 63 corrective actions required by the Federal Aviation Administration, which had investigated the incident. They installed a massive water deluge system, nicknamed the Steel Waterfall, under the launch pad. During engine ignition, this system dumps millions of gallons of water onto the pad to absorb acoustic energy and cool the steel. They strengthened the booster's engine shielding and improved the fire suppression system. They added more structural support to protect fuel lines from debris. All of these changes were made in about 7 months, a pace that would be impossible in traditional aerospace development. IFT-2, on November 18, 2023, showed the results. This time, all 33 Raptor engines started successfully and ran for the full duration of the booster's burn. The rocket performed hot staging for the first time, a complex maneuver where the second stage engines ignite while still attached to the booster, providing extra thrust before separation. This worked perfectly, and Starship separated cleanly and continued accelerating. The booster began its return, firing engines for the boost-back burn, but multiple engines failed, and the vehicle exploded over the Gulf of Mexico. Meanwhile, the Starship's second stage continued to climb, becoming the first Starship to reach space, crossing the Kármán line at 100 kilometers altitude. It also became, briefly, the heaviest object ever in space. The spacecraft continued accelerating for over 8 minutes. To simulate the propellant usage of a real mission, it was carrying extra fuel that needed to be vented before re-entry. During this venting process, liquid oxygen leaked and ignited, causing a fire in the aft section. The fire severed communication between the forward and aft flight computers, triggering a full shutdown of all 6 engines. The vehicle was lost, but not before providing invaluable data about hot staging, about how the stages interact during separation, about the behavior of cryogenic propellants in space. IFT-3, on March 14, 2024, demonstrated several mission objectives. The booster again performed well during ascent and staging. This time, it survived the boost-back burn, but failed to relight enough engines for the landing burn, exploding at an altitude of about 460 meters over the Gulf. The Starship spacecraft, however, achieved multiple firsts. It opened its payload bay door in space and closed it again, demonstrating cargo deployment capability. It performed a propellant transfer test, moving methane from a header tank to a main tank, a crucial step toward orbital refueling. It reached a peak altitude of 235 kilometers and began a controlled re-entry over the Indian Ocean. The vehicle survived deep into the re-entry heating phase before losing control and breaking up, but it had demonstrated that the basic heat shield concept worked. IFT-4, on June 6, 2024, was the breakthrough. Both stages completed their missions. The booster executed a controlled soft landing in the Gulf of Mexico, demonstrating that the flip maneuver and landing burns worked even without the tower catch. The Starship spacecraft survived the entire re-entry, despite catastrophic damage to its heat shield. Onboard cameras showed one of the forward flaps burned through almost completely, glowing white-hot and partially melting, yet the flight control software kept the vehicle stable. It completed a flip maneuver and achieved a soft vertical landing in the Indian Ocean. For the first time, a full mission profile had been completed. The path to operational reusability suddenly seemed real. Then came the moment that defined the program's progress. IFT-5, on October 13, 2024, attempted something audacious, catching the super heavy booster with the mechanical arms of the launch tower. Many experts thought this was too risky for a first attempt, that SpaceX should first demonstrate more ocean splashdowns before trying something so complex. But the SpaceX team had confidence in their simulations and their hardware. 7 minutes after liftoff, the booster approached the tower. Cameras captured it from every angle, this massive cylinder descending through the air, engines firing to control its speed and position, adjusting trajectory continuously as it aimed for the tower arms. And here's where the story gets truly dramatic. A detail that wouldn't emerge until days later when SpaceX engineers reviewed the flight data. During those final seconds of descent, one of the booster's health monitoring systems detected an anomaly. The flight computer, programmed with strict safety parameters, was processing whether to abort the catch attempt. If the abort command had been issued, the booster would have been ordered to divert and crash into a designated patch of ground next to the tower, rather than risk destroying the entire launch infrastructure. The margin? 1 second. The booster was literally 1 second away from that abort command when the sensor anomaly cleared and the catch was allowed to proceed. In that heartbeat of time, the arms closed around the booster, the engines shut down, and the vehicle hung there, suspended in the chopstick's grasp, smoke and heat shimmering around it. The control room exploded in celebration. "This is absolutely insane," shouted one of the engineers on the webcast. "On the first ever attempt, we have successfully caught the Super Heavy booster back at the launch tower." They had no idea yet how narrow their victory had been, how close the computer had come to pulling the plug, transforming their triumph into another learning opportunity, another data point on the long road to Mars. It truly was a day for the engineering history books. No one had ever caught a rocket booster out of the sky before. The implications were profound. Now, instead of landing the booster on legs miles away or in the ocean, requiring transport back to the pad, SpaceX could catch it at the launch site, inspect it immediately, and potentially refly it within hours. The dream of rapid reusability suddenly seemed achievable. But the path forward proved far from smooth. IFT-6, launched on November 19, 2024, attempted to repeat the booster catch with even more ambitious objectives, including an in-space Raptor engine relight test. President-elect Donald Trump attended the launch, standing alongside Elon Musk to witness what they hoped would be another historic catch. But as the booster descended toward the tower, something went wrong with the tower's sensors. Specifically, the chopstick arm sensors had been damaged during the launch itself, unbeknownst to the team. Without confidence in the tower's ability to safely execute the catch, the flight computer made the call. The booster was diverted to a controlled splashdown in the Gulf of Mexico instead. It landed softly on the water's surface, a successful demonstration of the backup landing profile, but not the triumph they'd hoped for. The Starship second stage, however, completed its mission perfectly, demonstrating the crucial ability to relight an engine in space, a capability essential for future orbital operations. IFT-7, on January 16, 2025, marked the debut of Block 2, representing the most significant upgrade to Starship's design yet. The booster, B-14, successfully performed another tower catch, redeeming the previous flight's disappointment. But Ship 33, the first Block 2 upper stage with its upgraded engines, larger propellant tanks, and redesigned forward flaps, met a different fate. 8 minutes and 20 seconds into flight, as the spacecraft continued its climb towards space, fire erupted in the aft section. The telemetry went dark. Contact was lost. 3 minutes later, the automatic flight safety system activated, and the vehicle disintegrated over the Caribbean in a spectacular shower of debris visible from the Bahamas to Jamaica. The investigation would later determine that stronger than anticipated vibrations during flight had stressed propulsion system hardware beyond its limits, leading to propellant leaks and the catastrophic fire. IFT-8 on March 6, 2025, demonstrated both the resilience and the challenge of Starship development. The booster, B-15, once again achieved a successful tower catch, the third such achievement proving the concept was repeatable. But Ship 34, the second Block 2 vehicle incorporating fixes from the IFT-7 investigation, suffered its own failure. At 8 minutes and 4 seconds into flight, roughly 30 seconds before planned engine cutoff, 4 of the 6 Raptor engines began shutting down prematurely. With only 2 engines remaining, both on the same side of the vehicle and unable to gimbal for thrust vector control. The spacecraft tumbled. Attitude control was lost. Telemetry ceased. The ship broke apart 9.5 minutes into flight, raining debris over Florida and the Bahamas in a display visible to startled residents who captured video of flaming fragments streaking across the evening sky. The cause this time was different from IFT-7, a hardware failure in one of the center Raptor engines that allowed propellant mixing and ignition where it should never occur, leading to an explosion that cascaded through the engine bay. 2 Block 2 ships, 2 different failure modes, 2 spectacular losses. Each flight, whether it ended in triumph or catastrophe, fed data back into the design process, driving changes, improvements, fixes. As you drift towards sleep, appreciate the pattern here. Not perfection, but iteration. Not flawless execution, but relentless learning. The explosions look dramatic, and they make for spectacular footage that ricochets around social media. But each one represents progress, a step closer to understanding this machine, to making it reliable, to turning it from a test article into an operational spacecraft that can carry people and cargo safely. As you drift towards sleep, appreciate the patience and persistence this testing represents. Think about the engineers reviewing telemetry data from a destroyed vehicle, identifying the failure mode, designing a fix, implementing it in the next prototype, and flying again. Think about the technicians welding new tanks, installing new engines, replacing damaged heat tiles, working around the clock to prepare the next vehicle. Think about the culture that says, it's okay to fail as long as we learn and improve. This is not how NASA conducted Apollo, where every mission had to succeed because failure would jeopardize the entire program and potentially kill astronauts. This is a different approach, possible only because SpaceX is building cheap enough hardware fast enough that they can afford to lose some vehicles during testing. The explosions look dramatic. They make for spectacular video clips. But each one represents progress, a step closer to understanding this machine, to making it reliable, to turning it from a test article into an operational spacecraft that can carry people and cargo safely. The journey from Starhopper's first hesitant hop to Starship's controlled re-entries and caught boosters is a story of learning through doing, of building, flying, exploding, analyzing, improving, and flying again. It's messy, it's expensive, but it's working. And with each flight, Starship becomes more capable, more reliable, more ready for the missions that lie ahead. Missions to orbit, to the moon, and ultimately to Mars. Catching a rocket, the chopsticks innovation. Stand back and watch a Starship booster return to the launch tower. First, you'll see the massive vehicle appear in the distance, a gleaming cylinder falling through the sky, trailing wisps of vapor. As it approaches, the roar of its engines reaches your ears. 3 Raptor engines firing in precise coordination to control its descent. The vehicle is moving fast, hundreds of kilometers per hour, but decelerating continuously as the engines fight against gravity and momentum. It's descending at an angle, not straight down, but approaching the tower like an aircraft on final approach. Then, in the last few hundred meters, it makes its final adjustments. The engines gimbal slightly, correcting trajectory. The vehicle rotates subtly, aligning itself with the tower. And there, extending from the launch tower like arms reaching out to embrace a falling child, are the chopsticks. These aren't delicate instruments. They're massive steel structures, each arm roughly 18 feet tall and strong enough to catch and hold a booster weighing hundreds of tons. They're positioned on the Mechazilla Tower, SpaceX's nickname for the launch integration tower that serves multiple functions: assembling the rocket before launch, providing propellant connections, housing flight control equipment, and now catching the returning booster. The chopsticks are controlled hydraulically, with the ability to move inward, or outward, gripping or releasing the booster as needed. They're precision instruments disguised as industrial machinery. As the booster approaches, it aims for a specific point in space between the arms. This requires extraordinary precision. The vehicle is approaching at speeds that would be fatal if it crashed, but it needs to slow to almost zero velocity just as it reaches the catch point. Too fast, and the arms can't safely absorb the impact. Too slow, and the engines might flame out before the catch is complete. The targeting must be accurate to within centimeters, threading the needle between the two arms while maintaining perfect vertical orientation. It's like landing a helicopter on a moving aircraft carrier, except the helicopter is 71 meters tall, weighs several hundred tons, and is being balanced on a column of rocket exhaust. How does it work? Let's break down the systems involved. As the booster separates from Starship, it begins falling back toward Earth. Initially, it's in a ballistic trajectory, following the path that physics dictates for an object thrown up and falling back down. About a minute after separation, the booster fires 13 of its engines for what's called the boost-back burn. This reverses its trajectory, sending it back toward the launch site. After the boost-back burn, the booster is on a path that will bring it near the tower, but it's still traveling fast and still at high altitude. During the descent, the vehicle uses small thruster systems, called reaction control thrusters or cold gas thrusters, to make fine adjustments to its orientation. These are much smaller than the main engines, using compressed nitrogen gas instead of methane and oxygen. But they can provide precise attitude control without the complexity of gimbaling the big engines. The flight computer is constantly calculating the booster's position, velocity, and rotation, comparing it to the planned trajectory, and making tiny corrections. As the booster approaches the landing zone, it enters what's called the landing burn phase. 3 engines reignite, chosen from the center cluster because they can gimbal for steering. These engines slow the vehicle's descent, fighting against gravity to bring the speed down. The timing here is critical. Fire the engines too early, and you waste propellant and might run out before you complete the landing. Fire them too late, and you can't slow down in time. The flight computer manages this balance automatically, adjusting thrust levels in real time based on the vehicle's actual performance. Meanwhile, the tower is waiting. Sensors on the tower and on the booster are communicating, exchanging data about positions and velocities. The chopstick arms are positioned in their open configuration, creating a gap that the booster will descend through. As the booster enters the final approach, it's moving at perhaps 50 or 60 kilometers per hour, maybe slower, descending through the air with engines throttled to balance its weight. At just the right moment, when the vehicle is positioned correctly and moving at the right speed, the arms move inward. The timing must be perfect. Move too early, and you might clip the booster as it's still descending, causing a crash. Move too late, and the booster drops past the catch point. When it works, and on Flight 5 and Flight 6 it did work perfectly, the arms close around hard points built into the booster's frame, just below the inner stage. These hard points are reinforced areas designed to take the load of being caught. The arms grip them securely, and the booster's engines shut down. In an instant, the vehicle transitions from a flying machine to a piece of cargo suspended in the tower's grasp. Shock absorbers and hydraulic systems in the arms dampen the forces involved, preventing the sudden stop from damaging the booster or the tower. It's a controlled catch, not a collision. Why go to all this trouble? Why not just land on legs like Falcon 9 does? The answer lies in the philosophy of rapid reusability. Landing legs add significant mass to the booster. They must be strong enough to support the vehicle during landing and robust enough to survive multiple reuses, which means they're heavy. Every kilogram of leg mass is a kilogram that could be payload. Moreover, legs require inspection and refurbishment after each flight. Hydraulic systems must be checked, shock absorbers examined, structures tested for stress fractures. This takes time and money. And perhaps most importantly, legs place the booster somewhere other than the launch pad after landing. If it lands on legs downrange or at a separate landing zone, you have to transport it back to the pad, which requires specialized equipment and more time. Catching the booster at the tower eliminates all of these issues. No legs means lower mass and less complexity. Catching at the launch site means the booster is already where it needs to be for the next flight. In theory, if the inspection shows the vehicle is in good shape, you could lift it back onto the pad, stack a new Starship on top, refuel, and launch again within hours. This is the vision, airline-like operations where the same booster flies multiple times per day. It sounds impossible, but that's what people said about catching the booster in the first place. The development of the chopstick system was not straightforward. Early concepts for Starship recovery involved legs, similar to Falcon 9. But Musk became convinced that catching was the better approach. In various presentations and tweets from 2019 and 2020, he described the concept. The booster would descend between the arms would close, and the vehicle would be held suspended. He acknowledged that the probability of success was uncertain, but above zero, a characteristic Musk understatement. Engineers at SpaceX spent years working on the mechanical systems, the hydraulics, the sensors, the software to make it work. The tower itself is a marvel of construction. It stands over 140 meters tall, taller than the fully stacked rocket it supports. It's built from steel beams and trusses, designed to withstand the forces of launch, the exhaust from 33 engines, the weight of the rocket being assembled, and now the impact of catching a falling booster. The chopstick arms are mounted on rails that allow them to move up and down the tower during rocket assembly and to extend inward during the catch. Multiple cameras on the tower and the ground provide visual feedback to the operators and the flight computer. Telemetry from the booster streams in continuously, updating the catch algorithms with real-time position and velocity data. On October 13, 2024, when Flight 5 attempted the catch for the first time, the SpaceX team had conducted extensive simulations. They'd modeled the trajectory, the timing, the forces involved. They'd tested the mechanical systems on the ground. But until that moment when the booster actually descended toward the tower with the arms open, they couldn't be absolutely certain it would work. Thousands of criteria had to be met, both on the vehicle and at the tower. If any of those criteria weren't satisfied, the booster would have been redirected to a splashdown in the Gulf of Mexico, just like the previous flights. But every system checked out. The booster approached, the arms closed, the catch was successful, and spaceflight changed. The reactions were swift and enthusiastic. NASA Administrator Bill Nelson congratulated SpaceX, saying, "Congratulations to SpaceX on its successful booster catch and 5th Starship flight test today. As we prepare to go back to the moon under Artemis, continued testing will prepare us for the bold missions that lie ahead." Engineers around the world recognized what had been achieved. This wasn't just an incremental improvement. It was a new capability, a fundamentally different way of recovering rocket boosters that could enable much faster and cheaper reusability. The successful catches on Flights 5 and 6 validated the concept. SpaceX has now caught a booster twice, demonstrating that it wasn't a lucky fluke, but a repeatable capability. Of course, not every attempt will succeed. Flight 6's booster catch worked, but during Flight 7, one of the commit criteria was not met, and the booster was diverted to an ocean splashdown instead of a catch attempt. This shows that SpaceX is willing to prioritize safety, only attempting the catch when all systems are nominal. But as the system matures, as the engineers gain more experience and confidence, the success rate should increase. Looking forward, SpaceX has even more ambitious plans. The chopsticks are designed not only to catch boosters, but eventually to catch the Starship second stage as well. In a talk in November 2024, Starbase General Manager Kathy Luters announced that SpaceX hoped to be able to catch a Starship upper stage sometime within the next 6 months, though this target has since been revised. Catching both stages would complete the vision of full reusability. Both stages return to the pad, both ready for rapid reflight, eliminating the need for any expendable components. Imagine the scene at Starbase if this vision is realized. A fully stacked Starship launches, ascending on a pillar of flame. Minutes later, the booster returns and is caught by the tower. An hour after that, the Starship's second stage, having completed its mission in orbit, re-enters the atmosphere, survives the fiery descent, and approaches the same tower. The arms, having released the booster, position themselves to catch the incoming spacecraft. It descends, engines firing, and is caught just like the booster was. Both stages are now at the launch site. Crews swarm over them, inspecting, refueling, replacing heat shield tiles if needed. Within days, perhaps within hours, they stack them together again and fly. This is the future SpaceX is building toward, and the chopsticks are the key technology that makes it possible. As you close your eyes tonight, picture those arms, massive and yet precise, reaching out through the air to catch hundreds of tons of falling metal and fire. Picture the engineers who designed them, who calculated the forces, who wrote the software, who built the hydraulics. Picture the controllers watching telemetry screens, monitoring the descent, ready to abort if anything looks wrong, but hoping, always hoping, that this time everything will work. And picture the moment of catch, when motion stops, when the booster hangs suspended, when the impossible becomes routine. That's the power of the chopsticks, and that's the future they represent, where rockets are caught from the sky and reused, where space is not a destination but a highway, where the barriers between Earth and orbit melt away under heat of progress and the cold precision of engineering. Beyond Mars, Starship's many missions. When you see Starship on the launch pad or ascending into the sky, it's easy to think of it as a Mars rocket, a machine built for one grand purpose. And certainly, that is the ultimate goal, the long-term vision that drives its development. But Starship is not a single-purpose vehicle. It is a platform, a versatile spacecraft that can be configured for dozens of different missions, each leveraging its enormous payload capacity, its full reusability, and its ability to operate both in Earth's atmosphere and in the vacuum of space. Let's explore these missions, from the mundane to the magnificent, from satellite launches to lunar landings, from point-to-point Earth transport to deep space exploration. Because understanding Starship's versatility helps us see why it represents not just a Mars rocket, but a new era in spaceflight. Let's begin with the most immediate application, deploying satellites. SpaceX's Falcon 9 rocket currently launches batches of 60 Starlink internet satellites at a time, gradually building out a constellation that now numbers in the thousands and aims to provide global broadband coverage. Starship could launch 400 Starlink satellites in a single flight, according to estimates from SpaceX, thanks to its vastly larger payload capacity. Think about what this means for the economics of satellite deployment. Instead of dozens of launches to deploy a large constellation, you might need only a handful. The cost per satellite drops dramatically. The deployment time shrinks from years to months. And this isn't limited to SpaceX's own satellites. Commercial customers who want to deploy large constellations could use Starship to do it faster and cheaper than ever before. The spacecraft's large payload fairing, 9 meters in diameter and up to 18 meters high, with approximately 1,000 cubic meters of usable volume, means it can carry payloads that simply wouldn't fit in any existing rocket. Want to launch a fully assembled space telescope? Starship can do it. The James Webb Space Telescope had to be folded and carefully packaged to fit into the Ariane 5 rocket's fairing, a complex and risky process. With Starship's generous fairing, future telescopes could be launched already assembled, reducing complexity and risk. According to reports, the Habitable Worlds Observatory, a future NASA space telescope designed to search for signs of life on exoplanets, is being designed with the assumption that large launchers like Starship will be available, allowing it to use glass mirrors instead of lighter but more expensive beryllium, and to be larger and more capable overall. Then, there's the International Space Station. SpaceX currently resupplies the ISS using its Dragon capsule, which can carry about 6,000 kilograms of cargo in its pressurized section. Starship could carry vastly more, potentially tens of tons of supplies and equipment in a single flight. This could simplify logistics for the station and reduce the number of resupply missions needed. Looking further ahead, when the ISS is eventually retired, Starship could help deploy replacement space stations, either by launching large modules that are assembled in orbit or by using Starship itself as a temporary habitable module. But perhaps the most concrete near-term mission for Starship is one that came as a surprise to many: landing humans on the moon for NASA's Artemis program. In April 2021, NASA awarded SpaceX a $2.89 billion contract to develop a version of Starship as the human landing system for the Artemis program. This contract was initially controversial. NASA had planned to select 2 companies to develop lunar landers to maintain competition, but budgetary constraints led them to choose only SpaceX. Blue Origin and Dynetics protested the decision, but after months of legal battles, the Government Accountability Office upheld NASA's selection and work proceeded. The Starship Human Landing System, or HLS, is a specialized variant designed specifically for lunar missions. It will launch on a super heavy booster and enter Earth orbit, where it will be refueled by multiple tanker starships. Once fully fueled, it will boost itself into a highly elliptical orbit around the moon called a near rectilinear halo orbit. There, it will wait, serving as a reusable ferry between lunar orbit and the surface. When Artemis astronauts arrive on the Orion spacecraft launched by NASA's Space Launch System, they will dock with Starship HLS, transfer aboard, and ride it down to the lunar surface. The Starship HLS is unique in several ways. Unlike traditional lunar landers like the Apollo LEM, which had separate descent and ascent stages, Starship HLS is a single vehicle that performs both functions. It's also enormous, about 165 feet tall, even without a booster, making it by far the largest lander ever designed. The crew will ride an exterior elevator down to the surface, descending from a height of about 30 meters. The vehicle doesn't need a heat shield or the complex flaps used for Earth atmospheric entry, since the moon has no atmosphere. But it does need special landing engines, high-thrust engines positioned higher on the vehicle to avoid kicking up too much lunar regolith during touchdown. The Artemis 3 mission, currently targeted for no earlier than 2026, though likely to slip to 2027 or later, will use Starship HLS to land astronauts near the moon's south pole, where frozen water may exist in permanently shadowed craters. Those astronauts, who would be the first humans on the moon since 1972, and will include the first woman and the first person of color to walk on the lunar surface, will spend about 7 days on the surface, conducting 5 or more extravehicular activities. After their mission is complete, they will climb back into Starship, ascend to orbit, and rendezvous with the Orion spacecraft for the return to Earth. NASA has already awarded SpaceX a second contract, called Option B, valued at approximately $1.15 billion, for a Starship HLS that will be used on Artemis 4 and potentially beyond. This version will be required to dock with NASA's planned Gateway Lunar Space Station, accommodate 4 crew members instead of 2, and deliver more cargo to the surface. It represents the beginning of a sustained lunar presence, with regular missions using reusable landers to build up infrastructure on the moon. But Starship's applications go beyond cargo and crewed missions. One of the more speculative but intriguing possibilities is point-to-point travel on Earth. Imagine boarding a Starship in New York, launching into a suborbital trajectory, and landing in Tokyo less than an hour later. The physics work. A rocket in ballistic flight can reach the opposite side of the Earth in about 40 minutes, far faster than any airliner. Musk has mentioned this application in various presentations, describing it as high-speed long-distance travel for cargo or potentially passengers. There are obvious challenges: regulatory approval, landing pads near cities, the noise and disruption of rocket launches, the safety considerations of flying passengers on rockets. But if these can be overcome, Starship could revolutionize long-distance transportation. There's also space tourism. While SpaceX has not announced specific plans for flying tourists on Starship, the spacious interior and fully reusable design make it well-suited for the application. Blue Origin and Virgin Galactic are already flying tourists on suborbital hops, brief tastes of weightlessness, and views of Earth from the edge of space. Starship could offer orbital tourism, multi-day stays in space with extended time to experience microgravity and see Earth from above. Japanese billionaire Maezawa Yusaku has already booked a flight around the moon on Starship, a mission called Dear Moon that will carry him and a group of artists on a circumlunar trajectory, though the mission has faced delays and its status as of 2025 is uncertain. Looking further ahead, Starship could enable entirely new categories of space activity. On-orbit manufacturing and construction, for example. Certain materials and processes work better in microgravity, manufacturing ultra-pure crystals for pharmaceuticals or fiber optics, for instance. Starship could deliver equipment and materials to orbit cheaply enough that space-based manufacturing becomes economically viable. Similarly, large structures like solar power satellites or space stations could be assembled in orbit using components launched on multiple Starship flights. There's also planetary defense. Asteroids occasionally pass close to Earth, and while the likelihood of a catastrophic impact is low, it's not zero. Starship could carry equipment to deflect or destroy a threatening asteroid, either by delivering a kinetic impactor to knock it off course or by placing propulsion systems on the asteroid to slowly alter its trajectory. The large payload capacity means you could send heavy equipment, multiple spacecraft for redundancy, or even a crewed mission if human presence were needed. And of course, there's Mars. We've talked about Mars colonization, but before colonies come exploration missions. Starship could deliver large rovers, scientific instruments, drilling rigs to search for water, equipment to manufacture propellant from Martian resources, and eventually, habitats for human explorers. Each Starship can carry over 100 tons to the Martian surface, enough to deliver everything needed for a comprehensive science mission, or the initial infrastructure for a permanent base. And because Starship is designed to return from Mars using propellant manufactured on the surface, it could bring back samples, data, and eventually, the crew. Even missions beyond Mars are possible. Starship has enough Delta V, with orbital refueling, to reach the moons of Jupiter or Saturn. It could deliver orbiters, landers, or even submarines to explore the subsurface oceans of Europa or Enceladus, where liquid water and perhaps life might exist. These would be one-way missions, as returning from that distance would require far too much propellant, but the scientific payoff could be immense. As you let your mind wander through these possibilities, appreciate the versatility that comes from designing a truly reusable, fully capable spacecraft. Starship is not optimized for any single mission. It's optimized for all of them. A platform that can be configured and reconfigured, equipped and re-equipped, launched and relaunched to serve whatever purpose we need. It's a truck, a taxi, a cargo hauler, a passenger liner, a ferry, a crane, all rolled into one gleaming stainless steel package. And that versatility, more than any single capability, is what makes it revolutionary. Not just a rocket, but the rocket. The vehicle that could finally make space accessible, affordable, and routine. The Raptor engine, heart of the beast. Deep within the engine bay of a Starship, beneath the gleaming steel skin and the maze of propellant lines, beats the heart of this incredible machine. Not one heart, but dozens, each a masterpiece of engineering that pushes the boundaries of what's possible with chemical rockets. These are the Raptor engines, and they are unlike any rocket engines that have flown before. To understand why Starship can achieve what it does, why it can lift such enormous mass, why it can return and fly again, you must understand these engines. So let's descend into the heat and noise and physics of the Raptor and see what makes it special. A rocket engine is, at its core, a device for turning chemical energy into kinetic energy. You take fuel and oxidizer, burn them together in a combustion chamber to create hot, high-pressure gas, and then exhaust that gas through a nozzle at high speed. The nozzle accelerates the exhaust, gases, and by Newton's third law, the rocket accelerates in the opposite direction. Simple in principle, fiendishly complex in practice. The key to an efficient rocket engine is the combustion chamber pressure. Higher pressure means the gases are more energetic when they enter the nozzle, which means they can be accelerated to higher speeds, which means more thrust for the same amount of propellant. But high pressure is hard to achieve and harder to sustain. You need powerful pumps to inject the propellants into the chamber against that pressure. You need materials that can withstand the heat and stress. You need seals that don't leak despite extreme conditions. Most rocket engines operate at chamber pressures between 50 and 200 bar, where 1 bar is roughly equal to atmospheric pressure at sea level. The Raptor engine operates at 300 bar. Some variants have reached even higher pressures during testing. This is the highest chamber pressure of any operational rocket engine in history, surpassing even the Russian RD-180, which held the previous record at about 265 bar. How does SpaceX achieve this? The answer lies in a combustion cycle so complex that only 2 other engines have ever attempted it, and neither flew successfully. It's called full-flow staged combustion. To understand full-flow staged combustion, we first need to understand the problem it solves. Remember that you need powerful pumps to get propellants into the chamber. These turbopumps are driven by turbines, which are spun by hot gases. Where do you get those hot gases? The most common approach, used in engines like the Falcon 9's Merlin, is called a gas generator cycle. You burn a small amount of fuel and oxidizer in a separate gas generator to create exhaust that drives the turbine, and then you dump that exhaust overboard, out the side of the engine. It's simple and reliable, but inefficient, because you're throwing away some of your propellant without using it to generate thrust. A more efficient approach is staged combustion, where instead of dumping the turbine exhaust overboard, you route it into the main combustion chamber. This way, all your propellant is burned twice, once in the preburner to drive the turbine, and again in the main chamber to generate thrust. The problem with staged combustion is that the turbine exhaust entering the main chamber is hot and chemically aggressive. If you run an oxygen-rich preburner, the exhaust is loaded with hot oxygen, which can corrode turbine materials. If you run a fuel-rich preburner, you avoid the corrosion, but you're burning fuel inefficiently in the preburner. Most staged combustion engines use one or the other approach. Full-flow staged combustion uses both. There are 2 preburners, one that runs oxygen-rich to power the oxygen turbopump, and one that runs fuel-rich to power the fuel turbopump. Both exhaust streams are then routed into the main combustion chamber, where they mix and burn completely. This is incredibly efficient because you're burning all of your propellant twice, and you're doing it in a way that minimizes the temperature in the turbines, allowing them to last longer. But it's also incredibly complex. You need 2 preburners operating at different mixture ratios. You need seals that prevent oxygen from leaking into the fuel side, or vice versa. You need precise control to keep both sides balanced. It's a nightmare to develop. Before Raptor, only 2 engines had ever attempted full-flow staged combustion. The Soviet RD-270 project in the 1960s built and tested a full-flow engine, but never flew it. Aerojet Rocketdyne's integrated powerhead demonstrator in the 2000s tested the powerhead, the assembly of pre-burners and turbopumps, but never a complete engine. Raptor is the first full-flow staged combustion engine to fly. The benefits are substantial. Because all the propellant is burned in the main chamber, efficiency is maximized. Because the turbines operate on relatively cool exhaust from fuel-rich or oxygen-rich pre-burners, they experience less thermal stress and can last longer, which is critical for an engine designed to fly many times. And because you're passing all the propellant through turbines before it reaches the chamber, you can achieve very high chamber pressures without needing impossibly powerful pumps. Raptor also uses methane as its fuel, specifically liquid methane at cryogenic temperatures. Most rocket engines use either hydrogen or kerosene, known in the industry as RP1. Hydrogen is very efficient, but has a low density, meaning you need large tanks to store it. And it's difficult to handle because it's so cold and leaks through the smallest gaps. Kerosene is dense and easy to handle, but burns dirty, leaving carbon residue that must be cleaned out of the engines between flights, which slows down reusability. Methane is a compromise. It's denser than hydrogen, making tanks smaller. It burns cleaner than kerosene, producing less residue, which simplifies reusability. And critically, it can be manufactured on Mars from atmospheric carbon dioxide and water, using a process called the Sabatier reaction, which is essential for Musk's vision of a self-sustaining Mars colony. The Raptor engine has gone through several iterations. Raptor 1, the initial production version, produced about 2 meganewtons of thrust, or about 185 tons force. It was used on the early Starship prototypes and the first few integrated flight tests. Raptor 2, introduced around 2021, was simplified with fewer parts, making it easier to manufacture and maintain. It produced about 2.3 meganewtons of thrust, 230 tons force, and became the standard engine for both Super Heavy and Starship. Raptor 3, unveiled in 2025, is even more advanced. According to statements from Elon Musk, it produces around 2.5 meganewtons or more, 250 plus tons force, is lighter than Raptor 2, and incorporates regenerative cooling directly into the engine structure, eliminating the need for external heat shields and fire suppression systems. It's described as having more thrust, higher efficiency, and simplified design. Truly, as Musk said, a work of art. Each Raptor is about 1.3 meters in diameter and 3 meters tall. It's compact compared to the thrust it produces, which allows SpaceX to pack many of them into a small space. This is important for Super Heavy, which needs 33 engines, but only has a 9-meter diameter to fit them in. The compact size comes from the high chamber pressure. More pressure means more thrust from a smaller combustion chamber. The engine is designed for reusability, targeting 1,000 flights per engine according to SpaceX's goals. To achieve this, components are over-engineered to handle the stresses of repeated thermal cycling, starting cold, heating to combustion temperatures, cooling down again. Turbopump bearings are designed for long life. Seals are tested to ensure they don't degrade. Cooling channels in the chamber walls use regenerative cooling, where cold propellant is pumped through tiny channels in the walls before it's burned, carrying away heat and protecting the chamber from melting. This is standard practice in modern rocket engines, but Raptor takes it to an extreme, handling the cooling loads from 300 bar combustion, with temperatures exceeding 3,000 degrees Celsius in the flame. One fascinating detail about Raptor is its gimbaling range, 15 degrees, higher than most engines. Gimbaling is the ability of the engine to pivot on its mount, directing thrust at an angle to steer the rocket. More gimbaling range means better control authority, which is crucial for a vehicle as large and dynamic as Starship. During landing burns, you can sometimes see the Raptor engines visibly tilting back and forth, making hundreds of tiny adjustments per second to keep the vehicle balanced. SpaceX manufactures Raptor engines at 2 facilities. The original production line is at their headquarters in Hawthorne, California, where they produce Raptor vacuum engines and experimental variants. In 2021, they opened a second facility in McGregor, Texas, near their rocket engine test facility, which focuses on serial production of Raptor 2 and later Raptor 3. The goal is mass production, making engines as quickly and cheaply as possible. Musk has stated that SpaceX aims to achieve a per-unit production cost of $250,000 per Raptor engine once mass production is fully ramped up. If achieved, this would make Raptor one of the cheapest rocket engines ever built in terms of cost per unit of thrust, a remarkable feat given its sophistication. The testing regimen for Raptor is intense. Each engine undergoes numerous hot fire tests on test stands at McGregor before it's shipped to Boca Chica for installation. These tests verify that the engine produces the correct thrust, that the combustion is stable, that there are no leaks or anomalies. Full duration burns simulate the conditions the engine will experience during flight. During Starship flight tests, engineers gather telemetry from every engine, monitoring temperatures, pressures, vibrations, looking for any sign of trouble. This data feeds back into the design process, informing improvements for the next iteration. As you drift toward sleep, imagine the complexity packed into each Raptor engine. Picture the fuel and oxidizer flowing through separate paths, each being pumped by turbo pumps spinning at tens of thousands of revolutions per minute. Picture the pre-burners, small combustion chambers where these propellants mix and burn just enough to create hot gas that spins the turbines which drive the pumps in a self-sustaining cycle. Picture those 2 exhaust streams, one oxygen-rich, one fuel-rich, meeting in the main combustion chamber and igniting in a furious, controlled explosion, creating a flame hotter than the surface of the sun. Picture this flame being channeled through a carefully shaped nozzle that accelerates it to supersonic speeds, producing thrust, lifting the vehicle, pushing it toward the stars. The Raptor engine is not just a component of Starship. It is the enabler of everything Starship does. Without Raptor's high thrust and high efficiency, the vehicle couldn't lift its massive weight. Without its reusability, rapid turnaround wouldn't be possible. Without its methane fuel, the Mars architecture wouldn't work. It is in every sense the heart of the beast, pumping power through steel arteries, turning fuel into motion, making the impossible real with every roar of its controlled fury. Life support and Mars architecture. Imagine you're on Mars. You step outside your habitat onto the rust-colored regolith. The sky is a butterscotch tan. Dust suspended in the thin atmosphere, scattering sunlight into unfamiliar hues. The sun looks smaller than it does from Earth, about 2/3 the apparent size, because Mars is half again as far from the sun. The temperature hovers around -60 degrees Celsius, though it might climb to a balmy 0 degrees at the equator on a summer afternoon. The atmospheric pressure is less than 1% of Earth's, so low that water boils at room temperature, and your blood would boil if you weren't wearing a pressure suit. And that suit, that thin envelope of fabric and technology, is all that stands between you and a quick, uncomfortable death. This is the environment that Starship must enable humans to survive in, not just for a brief visit, but for extended stays, and eventually permanently. Getting to Mars is challenging. Living on Mars is an entirely different order of problem. Let's explore the systems that will make it possible, from the life support equipment inside Starship during the journey to the infrastructure needed to sustain a colony once you arrive. Because Mars colonization isn't just about landing a rocket. It's about creating an entire ecosystem of technology, logistics, and resourcefulness that can keep humans alive, hundreds of millions of kilometers from Earth. Let's start with the journey. A trip to Mars takes between 80 and 150 days, depending on the trajectory and planetary alignment, with the average around 115 days. That's roughly 4 months locked inside a metal cylinder, with limited space, recycled air, freeze-dried food, and the knowledge that if something goes wrong, there's no turning back, no rescue mission, no emergency landing. The Starship Crew variant is designed to carry up to 100 people, though early missions might carry far fewer. Each person needs oxygen to breathe, water to drink, food to eat, and waste removal systems for the inevitable byproducts of biology. They also need radiation shielding, exercise equipment to prevent muscle and bone loss in microgravity, and enough space to avoid going insane from claustrophobia and interpersonal conflict. The life support system for a Mars Starship is based around what's called an Environmental Control and Life Support System, ECLSS for short. This is a suite of technologies that manages the spacecraft's internal environment. The key functions are oxygen generation, carbon dioxide removal, water purification, humidity control, and temperature regulation. Some of these are straightforward engineering problems that have been solved on the International Space Station. Others, like scaling up to support 100 people for months in a closed-loop system, represent significant challenges. Oxygen can be generated from water using electrolysis, splitting H2O into hydrogen and oxygen. The oxygen is released into the cabin atmosphere. The hydrogen is either stored for later use or vented overboard. Carbon dioxide exhaled by the crew must be removed from the air. Otherwise, it would build up to toxic levels within hours. This is done using chemical scrubbers, often based on lithium hydroxide, which reacts with CO2 to form lithium carbonate, or more advanced systems that use mechanical filters and regenerative processes. Water is perhaps the most critical resource. Humans need about 2 to 3 liters per day for drinking, plus more for hygiene, food preparation, and humidity control. Carrying enough water for 100 people for 115 days would require tens of tons, an impossible mass penalty. Instead, water is recycled. Urine, sweat, even moisture from the air, all are collected, filtered, and purified back into drinking water. The ISS achieves about 93% water recovery efficiency. A Mars Starship would need to match or exceed this. Food is simpler in one sense. You can store enough for the journey, but more complex in another. What do you store? How do you preserve it? How do you prepare it in zero gravity? Early Mars missions will likely rely on freeze-dried and dehydrated foods, similar to what astronauts eat on the ISS. Compact, lightweight, shelf-stable, and reasonably nutritious, if not particularly exciting. Longer term, there's interest in growing fresh food aboard the spacecraft, both for nutrition and for psychological well-being. But this is technologically challenging and not required for initial missions. Radiation is a more insidious threat. In Earth orbit, astronauts are protected by Earth's magnetic field, which deflects most cosmic radiation. On a journey to Mars, that protection is gone. The crew will be exposed to galactic cosmic rays, high-energy particles from distant supernovas and other cosmic events, and solar particle events, bursts of radiation from solar flares. Over months of exposure, the accumulated dose increases cancer risk and can cause other long-term health effects. Shielding helps, but is heavy. The most practical approach is to use the spacecraft's propellant and supplies as radiation shielding, arranging the interior layout so that tanks and storage areas surround the crew quarters, providing a buffer of mass. Water is particularly effective as shielding because it contains hydrogen, which absorbs radiation well. Once on Mars, the challenges multiply. The thin atmosphere provides almost no protection from radiation, so habitats will likely be buried under meters of regolith to provide shielding. The low atmospheric pressure means structures must be pressure vessels, constantly maintaining an internal pressure far higher than the outside. Any leak is a crisis. The cold means you need heating systems and insulation. The dusty environment means you need airlocks to prevent contamination of life support systems. Martian dust is fine, abrasive, and possibly chemically reactive, not something you want in your lungs or your equipment. And all of this infrastructure has to be delivered from Earth or manufactured on Mars from local resources. This is where in situ resource utilization, ISRU, becomes critical. ISRU is the practice of using local materials instead of bringing everything from Earth. On Mars, the most important ISRU application is propellant production. Starship uses liquid methane and liquid oxygen as propellants. Conveniently, Mars has the raw materials to make both. The atmosphere is about 95% carbon dioxide. Water ice exists at the poles and possibly underground in equatorial regions. Using the Sabatier reaction, you can combine carbon dioxide and hydrogen to produce methane and water. You can then electrolyze that water to produce hydrogen, which you recycle into the Sabatier process, and oxygen, which you store. It's a closed loop, requiring only energy and atmospheric CO2 as inputs. NASA's MOXIE experiment, which flew on the Perseverance rover, has successfully demonstrated oxygen production from Martian CO2. It's a small demonstration, producing about 10 grams of oxygen per hour, but it proves the concept works. A full-scale ISRU plant on Mars would need to be thousands of times larger, capable of producing tons of propellant to refuel a Starship for the return journey. SpaceX has stated that they plan to send ISRU equipment on early uncrewed cargo missions, setting up propellant production infrastructure before humans arrive. But propellant is just one application of ISRU. Martian regolith can be processed to extract metals like iron for construction, silicates for glass and concrete, and other useful materials. Water ice, if accessible, can be melted and purified for drinking, agriculture, and industrial processes. The atmosphere can be compressed and liquefied to provide nitrogen for habitat pressurization, mixing it with oxygen to create breathable air similar to Earth's. Even energy can be generated locally, using solar panels during the day and batteries for nighttime, or potentially small nuclear reactors for a more reliable baseload power. Agriculture on Mars is another challenge. Plants need light, water, carbon dioxide, nutrients, and the right temperature. Sunlight on Mars is weaker than on Earth, about 43% as intense due to the greater distance from the sun, but it's still sufficient for photosynthesis with the right crops. Greenhouses could use Martian soil as a growth medium, supplemented with nutrients, and treated to remove any toxic compounds like perchlorates, which are thought to be common in Martian regolith. Hydroponics, growing plants in nutrient-rich water without soil, is another option, potentially more efficient and controllable. Initial food production would supplement food shipped from Earth, but the long-term goal is self-sufficiency, where the colony grows enough food to feed itself. Musk has stated that he believes a Mars colony could achieve self-sufficiency, the ability to survive independently, even if supply missions from Earth ceased entirely, within 7 to 9 years of establishment. It's worth examining what this would actually require, and whether such a timeline holds up under scrutiny. The claim rests on several assumptions: that ISRU equipment can be deployed and operated successfully from the first cargo missions, that colonists can quickly establish food production through greenhouses and hydroponics, that essential manufacturing capabilities can be set up with the equipment brought from Earth, and that the colony grows rapidly enough to have the diverse skills and labor force needed to maintain complex systems. Based on what we know about the challenges of operating in hostile environments, from Antarctic research stations to offshore oil platforms, Achieving true self-sufficiency on Mars within a decade would represent an unprecedented accomplishment. These timelines seem to assume near-perfect execution of technologies that have never been tested in Martian conditions, rapid solving of problems as they arise, and a level of efficiency in colony establishment that historical precedent suggests might be optimistic. The actual timeline could be longer, perhaps significantly so, depending on how the first systems perform and what unforeseen challenges emerge. Yet the underlying concept that a Mars colony could eventually become self-sustaining is supported by the physics and chemistry of the situation. Mars has the raw materials needed: carbon dioxide in the atmosphere, water ice beneath the surface, minerals in the regolith, and solar energy available year-round. If the ISRU systems work as designed, if agriculture can be established, if manufacturing can be bootstrapped from local resources, then self-sufficiency transitions from impossible to extremely difficult, but theoretically achievable. The question becomes not whether it's possible, but how long it takes, and what it costs in resources, effort, and potentially lives. Consider the logic behind this timeline. The first missions deliver solar panels, ISRU equipment, habitats, rovers, and other infrastructure. The equipment begins producing propellant, water, and oxygen from local resources. Subsequent missions bring more equipment and the first crew. That crew sets up additional infrastructure, expands the ISRU operations, and begins construction of permanent habitats. More crews arrive on the next launch window, 26 months later, bringing expertise, supplies, and population growth. Within a few cycles, you have dozens or hundreds of people, megawatts of power generation, tons of propellant production per day, and enough food production to feed everyone. At that point, the colony can sustain itself even if Earth stopped sending resupply missions, which is the definition of self-sufficiency. Of course, this glosses over countless difficulties: medical emergencies with no hospital, equipment failures with no immediate resupply, psychological stresses of isolation and confinement, social dynamics of a small community living in an artificial environment. But each of these challenges is surmountable with planning, redundancy, and adaptability, qualities that SpaceX has demonstrated in its development of Starship itself. As you imagine life on Mars, picture not just the grand vision, but the daily reality. Waking up in a habitat module, the walls humming with the sound of air circulation fans, and the occasional creak of thermal expansion as the structure responds to temperature changes. Eating a breakfast of freeze-dried eggs, reconstituted with recycled water, perhaps with a side of fresh lettuce grown in the greenhouse. Suiting up in your pressure suit, checking seals and oxygen levels, then cycling through the airlock into the thin Martian atmosphere. Working outside to repair a solar panel damaged by a dust storm, the red landscape stretching to the horizon in every direction, the sky a pale ochre. Returning to the habitat as the sun sets, showering in a trickle of precious water, then gathering with your crewmates to review the day's progress, plan tomorrow's tasks, and maybe, just maybe, take a moment to look back at Earth through a telescope. A tiny blue dot hanging in the Martian night sky, a reminder of home. This is the future that Starship is being built to enable. Not just the journey, but the destination. Not just the landing, but the living. And every system SpaceX designs, every technology they test, every lesson they learn from Starship's development brings that future a little closer to reality. Challenges and criticisms. For all its promise, for all its achievements, Starship does not fly free of criticism. The program faces technical challenges that have not yet been fully solved, regulatory hurdles that slow development, environmental concerns from those who live near Starbase, and philosophical questions about whether Mars colonization is a worthwhile goal at all. To understand Starship fully, we must acknowledge these challenges and criticisms. Let's explore them not to diminish the program's accomplishments, but to see the full picture. The obstacles that remain, the voices that dissent, the problems that require solutions beyond engineering. Start with the technical challenges. Despite rapid progress, Starship is not yet operational. As of late 2025, no mission has achieved full reusability of both stages. The heat shield continues to lose tiles during flight, as seen in flight tests 4, 5, and 6. The engines, while improving with each iteration, have experienced failures during multiple flights. Ship 33 on Flight Test 7 and Ship 34 on Flight Test 8 both suffered engine failures that led to loss of the vehicle. These are not trivial issues. They represent fundamental engineering challenges in managing extreme temperatures, vibrations, and the stresses of launch and re-entry. The heat shield, in particular, has proven stubborn. 18,000 hexagonal tiles must adhere to the steel skin through launch vibrations. The thermal shock of cryogenic fuels, the aerodynamic buffeting of supersonic flight, and the searing heat of re-entry. SpaceX has tried various attachment methods, different adhesives and clips, gaps versus no gaps, ablative layers, felt padding between tiles. Each flight reveals new failure modes. Tiles pop off during ascent. Others fail during re-entry, allowing plasma to burn through into the structure beneath. While the system has proven robust enough that Starship can survive even with significant tile loss, as Flight Test 4 demonstrated, achieving the minimal maintenance and rapid reusability that SpaceX envisions will require a heat shield that doesn't require extensive inspection and repair after every flight. The Raptor engines, too, are still maturing. On Flight Test 7, a fire broke out during ascent that led to the loss of Ship 33. Investigation revealed that a leak in the engine system allowed fuel to escape and ignite. On Flight Test 8, 4 of Ship 34's 6 engines shut down prematurely during the ascent burn, causing the vehicle to lose control and break up. These failures occurred with Raptor 2 engines. The newer Raptor 3, with its simplified design and integrated cooling, is intended to be more reliable, but it has only begun flying as of late 2025, and any new engine design goes through teething problems before it matures. Then there's the schedule. Musk is famously optimistic about timelines, often projecting dates that SpaceX misses by months or years. Falcon Heavy was originally supposed to fly in late 2013. It didn't fly until 2018. The first crewed Dragon mission was originally planned for 2017. It happened in 2020. Starship orbital flight was originally targeted for 2020, and Musk at various points suggested humans could be on Mars by 2024 or 2026, dates that have come and gone. As of 2025, SpaceX has not yet achieved orbit with Starship, much less refueling, much less a moon landing, much less a Mars mission. The Artemis 3 mission using Starship HLS, originally planned for 2024, then 2025, is now targeting no earlier than 2026 or 2027 and may slip further. Some of these delays stem from technical challenges. Some stem from regulatory processes. The Federal Aviation Administration must approve each flight test, a process that involves environmental assessments, safety reviews, and sometimes mishap investigations. After Flight Test 1, the FAA required SpaceX to address 63 corrective actions before licensing the next flight, a process that took months. After Flight Test 7, another mishap investigation was required before Flight Test 8 could proceed. These regulatory requirements frustrate SpaceX, and Musk has publicly criticized the FAA for what he perceives as slow and overly bureaucratic processes. But the FAA's mandate is public safety, and they have a responsibility to ensure that rocket launches don't endanger people or property. Environmental concerns add another layer of complexity. Starbase is located in Boca Chica, Texas, a coastal area near wildlife refuges and nesting grounds for endangered species. The launch pad is less than a mile from the beach, and launches generate tremendous noise and heat. The explosions during Flight Test 1 scattered debris over a wide area, including into protected wetlands. Local residents and environmental groups have raised concerns about the impact on wildlife, particularly sea turtles that nest on nearby beaches and birds that use the area as habitat. The Fish and Wildlife Service and other agencies have required SpaceX to implement mitigation measures, including seasonal launch restrictions during nesting periods and environmental monitoring. The water deluge system installed after Flight Test 1 has also been controversial. It uses tens of millions of gallons of water during each launch, drawing from local aquifers and potentially affecting groundwater levels. While SpaceX has argued that the environmental impact is minimal and that they're working within permitted limits, environmental advocates continue to press for more stringent oversight and restrictions. There are also broader philosophical and ethical questions. Is it responsible to spend billions on Mars colonization when Earth faces urgent challenges like climate change, poverty, and disease? Musk argues that these are not mutually exclusive, that technological innovation, driven by space exploration, can have spin-off benefits here on Earth, and that becoming multiplanetary is essential for long-term survival of the species. Critics counter that resources devoted to Mars could be used more directly to address problems here and now, that space exploration, while inspiring, is a luxury when millions lack basic necessities. Some question whether Mars colonization is even desirable from an ethical standpoint. Should we be sending humans to a planet where survival will be difficult and dangerous, where they will face radiation exposure, isolation, and harsh conditions? Is it ethical to create a population dependent on constant resupply and technology to survive, knowing that if those systems fail, they will die? And if there is life on Mars, even microbial life, do we have the right to contaminate it with Earth organisms or disturb it with our presence? These are questions without easy answers, and they deserve serious consideration as the technology to reach Mars becomes real. There's also the question of governance. Musk has spoken about Mars being a free planet, a place where a new form of society could be established, potentially with direct democratic governance. But who decides how that society is structured? Who owns the land, the resources, the infrastructure? If SpaceX builds and operates the transportation system to Mars, do they have effective control over who can go and under what terms? These questions of governance and power will become increasingly important if Mars colonies actually begin to form. Safety is another ongoing concern. Rocketry is dangerous. SpaceX has lost multiple Falcon 9 boosters and several Starship prototypes. So far, all losses have been uncrewed test vehicles. But when humans start flying on Starship, whether to orbit, to the moon, or to Mars, the stakes become very different. The loss of a vehicle becomes a potential tragedy. SpaceX's philosophy of rapid iteration and accepting some failures works for development, but it must transition to a much higher standard of reliability for crewed missions. NASA's human spaceflight programs demand safety standards that SpaceX has not yet proven Starship can meet, though they are working toward it. And there are critics within the aerospace community who question whether the full reusability goal is achievable at the scale and cost SpaceX envisions. Some point out that even Falcon 9, SpaceX's most successful reusable rocket, requires extensive refurbishment between flights, limiting how often a single booster can fly. Applying this to a vehicle as large and complex as Starship, with its heat shield tiles and high-performance engines, might prove more difficult and expensive than anticipated. If rapid reusability can't be achieved, the economics of Starship change dramatically, and its advantages over other systems shrink. As you consider these challenges and criticisms, don't see them as reasons to dismiss Starship. but as acknowledgement of the difficulty of what SpaceX is attempting. Building a fully reusable super heavy lift launch vehicle that can carry 100 tons to orbit for a cost of a few $1,000,000 per launch, while also serving as a lander on airless worlds and a spacecraft for interplanetary journeys, is not a simple engineering problem. It's a collection of hard problems that interact in complex ways, each solution creating new challenges, each success revealing the next obstacle. And managing this development in the public eye, under regulatory scrutiny, with environmental considerations and ethical questions swirling around, adds layers of difficulty beyond the technical. But difficulty does not mean impossibility. SpaceX has consistently done things the industry said couldn't be done. They've changed what's possible more than once. And while challenges remain, while criticisms have merit, the progress is undeniable. Starship is flying. It's being caught. It's improving. The path forward is not smooth, but it is a path, and SpaceX is walking it, step by step, flight by flight, explosion by explosion, learning and adapting and pushing forward. Because that is what this endeavor demands. Not certainty, but persistence. Not perfection, but progress. Not answers, but the willingness to keep asking questions and seeking solutions. The Starbase story. Before Starship, before the launch pads in the factory and the crowds of spectators watching from South Padre Island, Boca Chica was a forgotten patch of coastal Texas. It was wetlands and dunes, scrub brush and saltgrass, home to ocelots and sea turtles and the occasional coyote. It was remote, accessible only by a single narrow road, surrounded by wildlife refuges and the Gulf of Mexico. It was, in many ways, the last place you'd expect to find the future of spaceflight. And yet, that's exactly where SpaceX built it. The choice of Boca Chica wasn't random. SpaceX had specific criteria for a site to develop and test Starship. It needed to be coastal, so that launches could head out over water rather than over populated areas. It needed to be at a southerly latitude, because launching from closer to the equator provides a boost from Earth's rotation, saving fuel. It needed space for large structures and test operations. And it needed to be somewhere that local authorities would welcome SpaceX rather than obstruct them with red tape and regulations. Texas, specifically Cameron County, where Boca Chica is located, met all these criteria. The state government was supportive, offering incentives and streamlined permitting. The land was cheap and relatively undeveloped. The location allowed launches to the east and south over the Gulf. And there was local enthusiasm for bringing jobs and economic development to an area that had struggled economically for years. In 2014, SpaceX began acquiring land and building infrastructure, and Starbase, as it would eventually be known, began to take shape. Initially, the site was modest. A few buildings, some concrete pads, storage tanks for propellants, a small test stand. SpaceX used it to test the Raptor engine and to fly Starhopper. But as the Starship program accelerated, Boca Chica transformed. The small test site became a sprawling industrial complex. Giant rockets began to rise from what had been empty fields. The sky filled with the roar of engines, smoke, and fire. One of the most striking aspects of Starbase is how visible the development process is. Unlike traditional aerospace facilities, which are heavily secured with restricted access, Boca Chica is relatively open. The main road runs right past the build site and launch pads. Enthusiasts can drive or bike to vantage points and watch construction and testing. This openness has created a community of Starship watchers, photographers, and citizen journalists who document every development, often sharing it in real time on social media. Websites like NASA, Spaceflight.com, and Lab Padre operate 24-hour webcams pointed at the site. Every time SpaceX moves a rocket section, or stacks vehicles, or conducts a test, thousands of people watch online. This transparency, whether intentional or simply a byproduct of the location, has generated tremendous public interest. People feel connected to the program in a way they never could with traditional aerospace projects hidden behind security fences and classified briefings. The community that has formed around Starship is passionate, knowledgeable, and deeply invested in the program's success. They celebrate the wins and mourn the explosions. They speculate about timelines and design changes. They've become an unofficial part of the testing process, documenting progress and sharing it with the world. The production methods at Starbase are unlike anything seen in aerospace before. Traditional spacecraft are built in carefully controlled cleanrooms, with components manufactured to exacting tolerances and assembled with meticulous care over months or years. Starship is built outdoors, in what's essentially a tent city. The build site is a sprawling area of tents and scaffolding where workers stack steel rings into cylinders, weld them together, attach engines and heat tiles, and prepare them for flight. It's more like a shipyard than a spacecraft factory. Noisy, dirty, fast-paced. This approach is intentional. SpaceX is optimizing for speed and cost, not cleanliness and precision. The philosophy is that it's better to build quickly and accept some imperfections, then learn from flight testing, rather than spend years perfecting a design on paper. And because they're building so many prototypes, they can afford to lose a few during testing without it being catastrophic. Each prototype costs millions, not hundreds of millions, because they're using relatively cheap materials, simple manufacturing techniques, and minimal overhead. The main production building, known colloquially as the mid-bay or high bay, is where nose cones and other complex sections are assembled. There's also the Star Factory, a massive expansion of manufacturing capacity that began construction in 2023. The Star Factory is designed to produce starships at a rate that approaches mass production, building vehicle sections on something like an assembly line, moving them through stations where different components are added or different processes applied. The launch infrastructure at Starbase consists of two orbital launch pads, OLP-A and OLP-B, and the towering Mechazilla integration and catch towers. OLP-A was the first operational pad, used for all the early integrated flight tests. OLP-B, a second pad built to allow for more rapid launch cadence, was still under construction as of late 2025. Each pad features a massive steel structure called the orbital launch mount, which supports the rocket before launch and contains systems for propellant loading, deluge water distribution, and engine ignition. The Mechazilla tower stands adjacent to the mount, its arms capable of stacking the vehicle before launch and catching the booster afterward. The propellant farm, a collection of large cryogenic storage tanks, holds liquid methane and liquid oxygen for fueling the rockets. These tanks are continually being expanded as SpaceX ramps up flight rates. There are also facilities for rocket engine testing, including a suborbital pad used for early Starship prototype hops, and multiple test stands for Raptor engines. Living and working at Starbase is an adventure. The nearest town is Brownsville, about 20 miles away, where many SpaceX employees live. But for those working long shifts at the site, especially during critical operations like rocket stacking or launch preparations, there are temporary accommodations on site or nearby. The work is intense. 7-day weeks are common during critical periods, with crews working around the clock to meet launch schedules. The environment can be harsh, hot, and humid in summer, occasionally cold in winter, with strong winds off the Gulf and swarms of mosquitoes. But for those who work there, there's a sense of purpose and excitement that's hard to find elsewhere. They're building the future, not hypothetically but literally, stacking rockets, testing engines, pushing the boundaries of what's possible. Many SpaceX employees speak about the culture of urgency and mission, the feeling that they're part of something bigger than a job, something that could change the course of human history. The impact on the local community has been significant. Boca Chica was a sleepy area with minimal economic activity. Now it's a focal point of the space industry. Jobs have been created, both directly at SpaceX and indirectly in supporting businesses. Hotels in Brownsville fill with space enthusiasts during launch tests. Restaurants see increased traffic. Real estate values have shifted as people move to the area for work or to be near the action. Some locals welcome this development, seeing it as economic opportunity. Others resent the disruption, the noise, the crowds, the changes to a place they knew as quiet and isolated. Environmental impact remains a contentious issue. Each launch is loud, a sonic assault that can be heard for dozens of miles. Debris from explosions, while mostly falling into the Gulf, has sometimes landed in protected areas, potentially disturbing wildlife. The lights and activity disrupt the natural rhythms of the coastal ecosystem. SpaceX has worked with regulators to mitigate these impacts, adjusting launch schedules to avoid nesting seasons, cleaning up debris, conducting environmental monitoring. But the tension between rapid development and environmental protection is ongoing, a balancing act that doesn't always satisfy anyone. In 2021, Musk announced plans to incorporate Starbase as a city, a move that would give SpaceX more control over local governance and development, but would also raise questions about corporate power and democracy. As of late 2025, the incorporation process was still proceeding, with debates about what kind of governance structure would be appropriate and what rights residents and workers would have. The long-term vision for Starbase is staggering. Musk has spoken of building multiple launch pads, enabling dozens or even hundreds of launches per year. The Star Factory expansion aims for production rates of 3 Starships per day, 1,000 per year. If achieved, Starbase would become not just a test site, but the primary launch complex for an interplanetary transportation system, the spaceport from which missions to the Moon, Mars, and beyond depart. Whether this vision materializes depends on countless factors: technical success, regulatory approval, continued funding, public support. But one thing is certain: Starbase has already transformed from a patch of empty Texas coast into one of the most important aerospace facilities in the world. A place where the impossible is attempted daily, where the future is being built one weld at a time, where steel and determination and vision are turning the dream of spacefaring civilization into metal and fire and progress. As you imagine this place, picture not just the rockets, but the people, the welders and engineers, the launch controllers and technicians, the dreamers and skeptics, all gathered in this remote corner of Texas, working toward a goal that most of humanity has yet to fully comprehend: making life multiplanetary, one launch at a time. Cut. Timeline to Mars and beyond. So when does it happen? When does Starship carry the first humans to Mars? When do the colonies begin? When does the dream, so often articulated, so thoroughly pursued, finally become reality? The answer, as with so much involving space exploration, is both closer and further away than you might think, filled with contingencies and dependencies, technical hurdles and regulatory approvals. Each milestone, a step on a path whose end is visible, but whose route is still being charted. Let's start with what we know, the concrete achievements and current plans, and build forward from there. As of late 2025, Starship has flown 11 integrated test flights. 11 times the stack has risen from Starbase on pillars of flame. 6 of those flights achieved at least partial success, demonstrating key capabilities. 5 ended in explosions or breakups, each providing lessons that informed the next attempt. The booster has been caught successfully twice. The spacecraft has survived re-entry multiple times. Orbital velocity has been achieved. These are not minor accomplishments. Each represents a hard-won advancement in our ability to build reusable spacecraft. The immediate goals for 2026 focus on operational maturation. SpaceX aims to demonstrate orbital refueling, the capability to transfer cryogenic propellants between 2 starships in orbit, a technology that has never been successfully demonstrated with methane and oxygen in space. NASA has required this demonstration as a prerequisite for the Starship HLS Critical Design Review, which must be passed before more funding is released for the Artemis lunar lander. Multiple test flights are planned to perfect this process, with a test campaign that should culminate in a ship-to-ship propellant transfer, proving that the concept works and establishing the procedures for future operational missions. If orbital refueling is demonstrated successfully, the next major milestone is the uncrewed Starship HLS demonstration mission, a flight to the moon where Starship lands, tests its systems on the lunar surface, and then returns to orbit. This mission, originally planned for 2025, has been delayed and is now expected in late 2026 or 2027. It's a crucial test, not only validating the landing systems, but also proving that Starship can operate in the lunar environment, that its engines can restart in vacuum, that its navigation and control systems can manage a descent, and landing on a world with no atmosphere. The crewed Artemis III mission, where astronauts land on the moon using Starship HLS, is currently targeted for no earlier than 2026, though most experts expect it will slip to 2027 or 2028. This mission will require multiple launches to put a Starship HLS in lunar orbit, tanker flights to refuel it, a successful SLS launch carrying astronauts in the Orion spacecraft, rendezvous and docking in lunar orbit, descent to the surface operations for about a week, ascent back to orbit, transfer back to Orion, and return to Earth. Each of these steps must work flawlessly because human lives will be at stake. The complexity is immense, and the margin for error is small. NASA and SpaceX are both deeply invested in making it work, but they're also realistic about the challenges. Beyond Artemis III, the Artemis IV mission in 2029 or later will use a second Starship HLS, this time docking with the Lunar Gateway Station and carrying 4 astronauts instead of 2. Regular lunar missions could follow, establishing a sustained human presence on the moon, with Starship serving as the reusable lander that ferries crews between orbit and surface, analogous to a lunar shuttle service. But what about Mars? Musk has long said that the first uncrewed starships could fly to Mars as early as the 2026 launch window, the period when Earth and Mars are optimally aligned, occurring roughly every 26 months. In September 2024, SpaceX announced plans to launch the first uncrewed Starship missions to Mars by 2026, aiming to send 5 starships to test whether they could reliably land intact on the Martian surface. This would be a one-way trip, demonstrating landing capabilities and delivering cargo, possibly including equipment for in situ resource utilization, habitats, power generation, or scientific instruments. If those missions succeed, SpaceX has stated they would begin crewed flights to Mars within about 4 years, putting the first humans on Mars around 2028 or 2030. However, as of May 2025, Musk updated this timeline, stating that SpaceX aims to target the 2026 to 2027 launch window if orbital refueling can be demonstrated successfully. He estimated a 50% chance of being ready in time for that window. If missed, the next opportunity would be in 2028-2029, with the overall timeline shifting by the 2-year gap between Mars windows. These are optimistic timelines, very optimistic. They assume that Starship matures rapidly, that orbital refueling works reliably, that Mars entry, descent, and landing can be perfected, that ISRU can be set up and operated remotely, and that all the life support and safety systems for a crewed mission can be developed and tested within a few years. Many experts outside SpaceX are skeptical. Traditional aerospace timelines for a crewed Mars mission have estimated launches in the 2030s or 2040s. SpaceX's approach, however, is to compress timelines by accepting higher risk, by building redundancy through numbers, by learning through doing, rather than analyzing to perfection. Consider the logic. If you send 5 starships to Mars in 2026, and 3 of them crash, you've still landed 2, providing valuable data and demonstrating that the basic concept works. If those 2 can deploy solar panels, start producing propellant, and send telemetry back, you've validated critical systems. On the next window, you send 10 starships, incorporating lessons from the first attempt. More land successfully. More cargo is delivered. Infrastructure accumulates. By the 3rd or 4th window, you might have enough equipment on Mars to support a crew, enough experience with landings to have confidence in safety, enough redundancy to handle failures. This is radically different from Apollo or any other crewed space program, where a single failure could end the program. SpaceX's approach is to treat vehicles as expendable during development, to build so many and launch so often that individual failures become acceptable, as long as the overall system improves. Whether this philosophy can be extended to crewed missions, where vehicle loss means loss of life, is a profound question that SpaceX will have to answer before astronauts climb aboard a Mars-bound Starship. Assuming the technical challenges are overcome and crewed Mars missions begin, the next phase is establishing a permanent colony. Musk's stated goal is a city of 1 million people on Mars by around 2060, using 1,000 starships launched during multiple Mars windows. This would require launching hundreds of starships every 26 months, delivering tens of thousands of people and hundreds of thousands of tons of cargo. It sounds impossible, but break it down. If Starbase and other future spaceports can support hundreds of launches per year, and if each launch costs only a few $millions due to reusability, and if Starship proves safe enough for large-scale human transport, the logistics become conceivable, if not easy. Each wave of colonists would build on the work of the previous wave. Early arrivals would set up power generation, ISRU, and basic habitats. Middle phase arrivals would expand agriculture, manufacturing, and infrastructure. Later arrivals would diversify the economy, culture, and society. Within a few decades, Mars could transition from an outpost dependent on Earth to a self-sustaining civilization, capable of feeding, housing, and supporting itself from local resources. But this vision assumes so many things go right. It assumes Starship becomes truly reusable with minimal refurbishment. It assumes launch costs drop to the levels SpaceX projects. It assumes enough people want to go to Mars, that they're willing to leave Earth forever for a harsh, dangerous life on another planet. It assumes governments don't restrict or prohibit such missions. It assumes the social, psychological, and political challenges of founding a new civilization can be managed. These are big assumptions. Yet even if the timeline stretches, even if the first million-person city takes a century instead of half a century, the trajectory is becoming clear. Starship is flying. It's improving. Its capabilities are growing. The path to orbit, to the moon, and yes, to Mars, is being built flight by flight, test by test, explosion by explosion. We may not know the exact date when the first human footsteps will mark Martian soil, but we can see that the technology to make it possible is being developed right now. And beyond Mars, the solar system opens before us. Starship's performance envelope includes not just Mars, but asteroids for mining, the moons of Jupiter and Saturn for exploration, even distant Kuiper Belt objects if we're patient and plan carefully. With orbital refueling and nuclear propulsion potentially added in the future, the range extends even further. We could build bases on moons, establish outposts in asteroid belts, create infrastructure that spans the inner solar system. And far in the future, perhaps Starship's descendants, refined and improved over decades or centuries, could be part of missions to other star systems, carrying human and robotic explorers toward distant worlds we can barely imagine today. This is the timeline to Mars and beyond. Not a straight line, but a winding path. Not a schedule, but an aspiration, not a guarantee, but a possibility. And that possibility, fragile as it is being built in the deserts of Texas and in the minds of engineers and dreamers around the world. One test flight at a time, one explosion learned from, one successful catch celebrated, one step closer to the stars. But here, as our journey together draws to a close, let me share one final truth that reframes everything you've heard tonight. A perspective that changes how we understand not just Starship, but why it matters. We've talked about Mars, about colonies and self-sufficiency and million-person cities on another world. We've discussed the engineering marvels, the explosive tests, the audacious catches, the relentless push toward a future among the stars. And all of that is real. And all of that matters. But perhaps the most important thing Starship represents has nothing to do with where it's going. Consider this. For the first time in human history, we are watching a civilization actively choose to become multiplanetary. Not because we must, not because Earth is immediately dying, not because an asteroid is bearing down on us next week, but because we can. Because a small group of people decided it was worth trying. Because someone looked at the impossible and said, "Not with that attitude." The real revolution isn't the rocket, it's the mindset. For decades, humanity accepted that space exploration would be slow, expensive, the exclusive domain of governments with enormous budgets, moving at the pace of political will and public funding. And then came a company that said, what if we just go faster? What if we test weekly instead of yearly? What if we embrace failure as data instead of catastrophe? What if we build 100 rockets instead of carefully crafting one perfect one? Every explosion you've heard about tonight, every crashed booster, every disintegrated Starship raining debris over the Gulf of Mexico represents a fundamental shift in how humanity approaches the hardest challenges. Traditional aerospace would have spent a decade analyzing the first failure, writing reports, convening panels, ensuring it never happened again. SpaceX launches again in 3 months, incorporating the lesson and finding the next problem to solve. And that, more than any specific technical achievement, is what makes Starship significant. It's demonstrating that the impossible becomes merely difficult when you change your approach to failure, when you build systems fast enough and cheap enough that you can afford to break them and learn. This philosophy is already spreading beyond rocketry. We see it in how people think about climate, change, energy, medicine, infrastructure. The message is clear. We are not trapped by the limits we've accepted. We are capable of more than we think we are. There's also this. Right now, somewhere, a child is watching a Starship launch, seeing that rocket rise on a column of flame and thinking, I want to be part of that. Maybe they become an engineer. Maybe they become a scientist. Maybe they study something completely unrelated, but carry with them the lesson that ambitious goals are worth pursuing, that the future can be shaped, that we don't have to accept the world as it is. The Apollo program inspired a generation. The images of astronauts walking on the moon sparked countless careers in science, technology, engineering. But Apollo ended. The missions stopped. The promise of space faded into budget cuts and political realities. For decades, children who dreamed of the stars grew up to find that humanity had seemingly given up on that dream, accepting Earth orbit as the new ceiling. Starship says, we're trying again. And this time, we're not stopping at flags and footprints. This time, we're building a transportation system. This time, we're going to stay. Whether Elon Musk's timeline for Mars comes true in the 2030s, or slips to the 2050s, or takes a century, whether the first colony has 1 million people or 1,000, whether SpaceX succeeds completely or hands the baton to another organization that builds on their lessons, none of that changes the fundamental truth that right now In this moment, humanity is actively working to become a spacefaring civilization. Not talking about it, not studying it, doing it, testing, flying, learning, building, and 1 second can change everything. Remember that moment we discussed at the start? The booster descending toward the tower, the sensor anomaly, the computer one heartbeat from aborting the catch? That's the perfect metaphor for this entire endeavor. We are always 1 second from failure, one decision from disaster, one mistake from losing everything we've built. But we're also 1 second from breakthrough, from triumph, from the moment when the impossible becomes real. The chopsticks closed, the booster was caught, the celebration erupted, and humanity took another step toward the stars, not knowing how close we'd come to a very different outcome, but knowing that the only way to reach Mars is to risk everything in the attempt. And now, as the details begin to blur and the technicalities fade into the background, let yourself simply float with the larger truth. Starship is not just metal and engines and careful mathematics. It is a choice, made by us, in our time, to reach beyond our current limits. It is a statement that we refuse to accept that Earth is all we'll ever know. It is fundamentally an act of defiance against the entropy and limitation that governs so much of existence. You've drifted with us through steel and fire, through failure and triumph, through sensor, anomalies, and successful catches, through explosions that taught lessons and tests that proved concepts. You've seen what happens when brilliant people decide that slow, careful progress isn't enough, that humanity deserves to move faster, reach farther, dream bigger. And whether you're still awake to contemplate these visions, or already fading into sleep with dreams of distant worlds, know that this story isn't over. It's still being written, one flight at a time, one iteration at a time, one bold decision at a time. The future is not predetermined. It is not a destination we arrive at passively. It is something we build, something we choose, something we fight for. And right now, in the coastal wetlands of South Texas, that future is being welded together, tested with fire, and launched toward the stars. If you enjoyed drifting through this exploration, consider subscribing to Sleepable Science. New journeys through science and wonder await. Sleep well, dream of rockets and stars and all the audacious futures we might build. And remember, the impossible is only impossible until someone proves otherwise. Good night, and may your dreams carry you to the stars.